Praveen, your chemistry educator. Students, in this video, what we are going to do, we are going to cover the full aldehyde, ketone and carboxylic acid chapter. Right? And you know very well, students, that in NEET examination, from this chapter, we get at least 3 questions every year. And you can confirm that anytime by your PYQs. If you look into the previous year questions of the NEET examination, you will find so many questions from this chapter, aldehyde, ketone and carboxylic acid. One more point. Please be careful. Like before you start the chapter aldehyde, ketone and carboxylic acid, so before starting this chapter, you should have the knowledge of the rest of the chapters of your organism, like haloalkanes, haloarenes and alcohol phenol ethers. Why? Because this chapter aldehyde, ketone and carboxylic acid, it is very much connected with the alcohol phenol ether chapter and haloalkanes and haloarenes. So in this video, I will be covering each and every point, each and every concept, whether it is from the preparation part, whether it is from the physical property part, whether it is from the chemical reaction part, right? And I will discuss each and every name reactions in this video, right? And I will also tell you some of the mechanisms of these reactions. But after completing this session, your task will be solving the DPP, solving more and more questions from this chapter, right? And what we are doing, we are providing you the DPPs in the description of the video. So from the description, you can download those DPPs, and also those DPPs you can get on the PW app. So download the PW app, and just like lakhs of students, you also start your NEET journey with PW. So let's start the session, students, with the very first thing, that is what are the topics that we are going to cover in this video, in this session. So we will start with the introduction of aldehyde ketone, like what is aldehyde according to structure, what is ketone according to structure, what is carboxylic acid according to structure. Then we will talk about some of the very important common names of aldehyde ketones, because you know that sometimes in your questions you get directly the use of common name, right? So some of the common names you need to memorize them, right? I will tell you what are the common names you need to memorize. Then I will talk about the preparation or the methods of preparations of aldehyde ketone. Then we will talk about the properties, that means physical properties as well as chemical reactions of aldehyde ketone. And after aldehyde ketone, because we are doing aldehyde and ketone together, so after aldehyde ketone, we will talk about carboxylic acid. So in carboxylic acid also we will have introduction, right? We will talk about some of the important common names of carboxylic acid. Then we will talk about how we can prepare the carboxylic acid. And after that, we will talk about properties of carboxylic acid, means again physical properties, and the chemical reactions of carboxylic acid. But you know very well that in carboxylic acid, apart from the preparation and chemical reaction, we have one more important topic, that is comparison of acidic strength of carboxylic acid, because you do get question from that also. So in this video, at the end, we will talk about what are the methods by which we can compare the acidic strength of carboxylic acid, right? So first of all, let's talk about the introduction, right? Means what do you mean by aldehyde and ketone? So for students, first point is, we have a class of compounds which are called as carbonyl compounds. You know it very well, right? It's very basic that when you have a compound which contains this group, C double bond O group, right? So this group itself is called as what? Carbonyl group. And aldehyde ketones, they are nothing but they are examples of your carbonyl compounds, right? Point is, in your carbonyl group, if you notice, so for your carbon, you have 2 free bonds, right? Now, out of these 2 free bonds, if one side around this carbonyl, on the one side, if you have an alkyl group, like alkyl group means it can be a open chain of carbon, it can be a closed chain of carbon, it can be aromatic ring, right? Anything. So if you have an alkyl or aryl group, and other side of carbonyl, you have hydrogen. So then this C double bond OH group is called as aldehyde. Similarly, around your carbonyl, both side if you have alkyl aryl group, so then it is called what? Ketone. And around your carbonyl group, one side if you have alkyl aryl group, but on the other side you have hydroxy group, OH group, right? So then it is called what? Carboxylic acid. But apart from aldehyde, ketone and carboxylic acid, we have more examples of carbonyl compounds. Like suppose that around your carbonyl, one side you have alkyl or aryl group, but on the other side you have alkoxy group. So then it is called what? Ester. Then it is called ester. You know it, ester very well, very well from your 10th class itself. Similarly, around your carbonyl, right? If you have a alkyl group and carboxylate group, right? So then this is called acid anhydride. Anhydride is very famous, right? Remember when we talk about IUPAC nomenclature. So in your IUPAC nomenclature, the nomenclature of acid anhydride you always discuss separately, because this is very important, right? And anhydride you can understand like this also, that we have two carbonyl group, in between them we have oxygen, and both sides we have alkyl or aryl group. Apart from anhydride, we have few more, like one is acyl halide or acid halide, which is very important. In acyl halide, what happens? Around your carbonyl, one side you have alkyl and aryl group, but on the other side you have a halogen like fluorine, chlorine, bromine and iodine, right? And one more, if you talk about amide, so you will see amide in your amine chapters. It is very common for your amine chapter. So amide is nothing but carbonyl, right? On the one side of carbonyl you have alkyl or aryl group, but on the other side you have the NH2 group, which you also call as amine group, right? So around carbonyl, if you have alkyl and aryl group, and other side you have NH2, then it is called what? Amide. But point is, all these amide, acyl halide, anhydride, ester, aldehyde, ketone, they are the examples of what? Carbonyl compounds. Collectively, they are called as what? Carbonyl compound. And out of all these carbonyl compound, in this video, first of all, we are going to focus more on aldehyde part and the ketone part, right? Now, let's see some of the common names of the aldehyde ketone, which is very important. One more thing, I hope that you people have covered the IUPAC nomenclature of aldehyde ketone in the GOC in the basic organic chapter, right? So for nomenclature, for IUPAC nomenclature, anytime you can refer to the GOC chapter class 11th, right? So here we are not talking about the IUPAC nomenclature, we are talking just about the common names of aldehyde ketone. Like if you see the very first compound, like benzene having a aldehyde group, right? And then you have a methoxy and alcohol group. So this is very famous, right? You eat ice cream, right? In ice cream you have some vanilla flavor, and we get vanilla flavor, we get vanilla essence from this compound, and this is called commonly vanillin. This is nothing but your vanillin. Okay, so after vanillin, the next compound we have is benzene connected with aldehyde and hydroxy group, right? At ortho position, and this compound is commonly called as salicylaldehyde. Salicylaldehyde, right? Then we have this very famous compound in which you will notice that you have a CC double bond. One side you have aldehyde group, one side you have phenyl group. So this is called cinnamaldehyde. This is called cinnamaldehyde. Then this one is very famous, right? CS3, C double bond O CS3. This is commonly called as acetone. Now, why we are talking about common names? Because most of the time in your questions, instead of using IUPAC name for these compounds, they will be using common names. So you need to identify that when they say acetone, what is the structure of acetone? So acetone is CS3 C double bond O CS3. Similarly, if you talk about this compound, right, in which carbonyl, one side we have methyl group, one side we have phenyl group. So this is commonly called as acetophenone. This is called acetophenone, right? Then this one, right, in which you have one side phenyl, one side you have 2 carbon. So this is called commonly propiophenone. Propio because we have 3 carbon here in the open chain. So propiophenone. Then this one is very famous again. Benzene both side around the carbonyl. This is called benzophenone. This is called benzophenone. Then this compound is very much famous, CH2 double bond CHCHO. It is called as acrolein. This is called acrolein. And again, benzene having 2 aldehyde groups together at ortho position. This is called thaldehyde. Like if you remember, in benzene at ortho position, if you have 2 carboxylic acid groups, COH, then it is called phthalic acid. So similarly, if you have 2 aldehyde group, so then it is called thaldehyde, right? So these common names, right, you should know, you should remember, whether it is vanillin, salicylaldehyde, cinnamaldehyde, acetone, acetophenone, propiophenone, right, benzophenone, and acrolein and thaldehyde. So after these common names, we should quickly go into the most important point in this chapter, and you know it very well, which is preparations of aldehyde and ketone. And if you talk about preparations of aldehyde ketone, students, right? So in this chapter, we have lots of preparation. If you compare the preparation of aldehyde ketone with alcohol or ether or phenol or haloalkane, haloarenes, right? So as compared to them, in this aldehyde ketone chapter, we have lots of numbers of preparation that we need to focus. But many of them are repeat. Like here we are talking about, first of all, we can prepare aldehyde ketone by the oxidation of alcohol. But point is, this reaction you must have seen in your alcohol chapter 2. So we are repeating this reaction. Point is, students, when you take alcohol, so alcohol can be classified according to degree as primary alcohol, secondary alcohol, tertiary alcohol. So point is, if you take primary alcohol, and you do oxidize that with some mild oxidizing agents like PCC or PDC. So PCC or PDC, it will oxidize the primary alcohol into aldehyde. It will oxidize the primary alcohol into aldehyde. Basically, you can memorize this, something like this, that when we do oxidation of primary alcohol, from the alpha carbon, one of the hydrogen will be removed, and from the oxygen atom, one of the hydrogen will be removed, and ultimately you will get a double bond between this alpha carbon and oxygen. So you will get a carbonyl group. Now point is, in case of 1 degree alcohol, instead of PCC, if you use a strong oxidizing agent like KMnO4, K2Cr2O7 or Jones reagent, so in that case, instead of getting aldehyde, you will be end up with getting carboxylic acid, right? So here it is better to use mild oxidizing agents like PCC, or instead of PCC, we can also use dry chromium oxide, dry CrO3. Dry CrO3 also, it can oxidize primary alcohol into aldehyde, right? And suppose if I am using strong oxidizing agent, right, for the oxidation of primary alcohol, still there is a way by which I can get aldehyde, but for that I will have to do distillation as soon as the aldehyde gets formed. Right? Now, to get rid of that, distillation thing, what we do, we use the PCC, the mild oxidizing agent, right? And for your examination, whenever they say that with 1 degree alcohol, if I use a strong oxidizing agent, so you people will always say that we will get what? Carboxylic acid. Now, point is, apart from 1 degree alcohol, if I use 2 degree alcohol, so in 2 degree alcohol, what will happen? On your alpha carbon, you will have only one hydrogen, right? So during the oxidation of 2 degree alcohol, what will happen? From alpha carbon, again this hydrogen will go out, and from your oxygen, again this hydrogen will go out, and again you will get a double bond between the carbon oxygen. So in this case, instead of aldehyde, you will end up getting a ketone, right? Instead of aldehyde with 2 degree alcohol, with secondary alcohol, you will be getting what? Ketone. So point is, by the oxidation of alcohol, we can prepare both aldehyde and ketone. Point is, if I chose primary alcohol, 1 degree alcohol, I will get aldehyde. If I chose secondary or 2 degree alcohol, so in that case, I will be getting what? Ketone, right? And you can't use 3 degree alcohol because 3 degree alcohols are difficult to oxidize, right? We need extreme condition for that. But under vigorous oxidation, 3 degree alcohol, it can also give you what? It can also give you ketone, right? But it is preferred to use primary and secondary alcohol. But point is, when you are oxidizing secondary alcohol, you can use any of the oxidizing agent. You can use PCC, PDC here. But apart from PCC, PDC, if I use strong oxidizing agents like KMnO4 or K2Cr2O7 or Jones reagent, which is basically CrO3 and H2SO4, right? So if I use a strong or mild, any oxidizing agent, I will end up getting what? Ketone. Because ketones are very difficult to get oxidized. So whether it is mild or strong, with 2 degree alcohol, you will be getting what? Ketone. So both aldehyde and ketone can be formed by the oxidation of alcohol. Now, I want you to remember one thing always, not regarding your strong oxidizing agent, but regarding your PCC. Students, please remember that PCC will not affect carbon-carbon multiple bond from your substrate. So in your substrate, if you have a carbon-carbon double bond, right, carbon-carbon triple bond, so that will not be affected by PCC because PCC is a mild oxidizing agent. So now we have understood that how we can get aldehyde ketone both by the oxidation of alcohol. So now let's talk about the next method. And before we go into the next method, we have a question here. So in this session, what I have done, with each and every concept, with each and every reaction, I have included a question. So what you can do, you can understand a concept and immediately after that, you can practice a problem, right? So if you want to do it by yourself, please pause the video, do it by your own, and later on you can match your answers with me, right? So we have a question here that identify the correct reagent that would bring about the following transformation. Now, what transformation we are happening here? What transformation is happening here, if you notice? So cyclic ring CH2 single bond CH double bond CH2, it is converting into cyclic ring CH2 single bond CH2 and CHO. Now overall, if you notice what is happening, this pi bond, it is converting into single bond, and this CH2 group, it is converting into CHO, right? So one by one, let's check the reagent. Students, in the first option, the first reagent is, if you remember, BH3 with H2O2 and OH minus, it is nothing but hydroboration oxidation reaction. And it is the reaction for your alkene. So for this alkene, if you do hydroboration oxidation, what you will get? You will get a lower degree alcohol, an alcohol, right, which looks like an anti-Markovnikov product, right? So in this substrate, if I use this BH3H2O2 OH-, I will get this product, cyclic ring CH2 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 OH, anti-Markovnikov product. Now later on, if I do oxidation with KMnO4, you know very well that KMnO4 is a strong oxidizing agent, and this is a 1 degree or primary alcohol. So with a primary alcohol, if I use KMnO4, it will give what? Carboxylic acid. Just now I told you that 1 degree alcohol with a strong oxidizing agent, it will convert into carboxylic acid. And 2 degree alcohol, right, with a strong oxidizing agent, it will convert into ketone. And if you want to convert 1 degree alcohol into aldehyde, you need to use mild oxidizing agent. So definitely from the first case, we can't get this aldehyde group. So first is not possible. Now, in the second case, if you notice, we are using acid catalyzed hydration. Now, when you do acid catalyzed hydration for this CC double bond, right, it will give you Markovnikov product, and the Markovnikov product after addition of water in your substrate will be CH2, CH, OH, CH3. So here you are getting what? 2 degree alcohol. Now point is, I don't have to check what oxidizing agent they are using, PCC or KMnO4. Point is, if I have a 2 degree secondary alcohol, and if I oxidize this, I can never get aldehyde from this. I will get ketone. So even the second option is not correct. And similarly, the third one. In third case also, first we are doing acid catalyzed hydration. So I will get 2 degree alcohol. And when I oxidize with CrO3, I can't get aldehyde, I will get ketone only. So definitely here, the answer will be fourth one, because for your substrate, when you do hydroboration oxidation, right, you get anti-Markovnikov product, which is 1 degree alcohol. And in your 1 degree alcohol, if you use PCC, right, so PCC will do the task. PCC will convert 1 degree alcohol into aldehyde, right? So from this, you can convert your substrate into your desired product. And definitely in this case, your answer will be fourth, that means option D. And yes, D is your answer. But point is, students, this question we got in the NEET 2024 examination. So it's a very recent question. And if you look at the details of the question, you require knowledge of only two things. First, hydration or hydroboration oxidation of alkene. And secondly, what is the way that alcohol gets oxidized in the presence of mild and strong oxidizing agent, especially for your 1 degree alcohol, because 1 degree alcohol with mild oxidizing agent, it gives aldehyde, like PCC, PDC, and with strong oxidizing agent, it gives you what? Carboxylic acid, like KMnO4, K2Cr2O7, right? Now, the second method of preparation of aldehyde ketone is again we have from alcohol only, but this time we are not going to perform oxidation. Instead of oxidation, what we do? We do dehydrogenation. Dehydrogenation means from your substrate, hydrogen atoms will be eliminated in the form of H2 gas. So point is, if you take a primary or 1 degree alcohol students, right, and if you do dehydrogenation, so dehydrogenation of alcohol is done using copper and some elevated temperature, like copper at some 573 Kelvin temperature, right? So what it will do? It will remove hydrogen from your carbon and oxygen, from your alpha carbon and oxygen. So from this alpha carbon and this oxygen, these hydrogens will be eliminated in the form of H2, and again a double bond will be created between carbon and oxygen. So you will be getting what? RCH double bond O. So here also, just like PCC, from this 1 degree alcohol, you are getting what? Aldehyde. And again, if I use 2 degree alcohol in this, so by the dehydrogenation of 2 degree alcohol with the same copper and heat, I will be getting what? Ketone. I will be getting ketone. But, if you remember, you cannot oxidize 3 degree alcohol easily, but dehydrogenation of 3 degree alcohol is very much possible. But point is, when you do dehydrogenation of 3 degree alcohol, you won't get aldehyde or ketone, you will be getting what? Alkene. So with 3 degree alcohol, it will be something like your dehydration reaction. If you remember the dehydration reaction of alcohol, especially the acid catalyzed dehydration, right? So similar product you will be getting from the 3 degree alcohol by the dehydrogenation process. But still, from 3 degree alcohol, we can't prepare what? Aldehyde ketone. Again, from 1 degree alcohol, we get aldehyde, and from 2 degree alcohol, we get ketone. So this copper at some high temperature, right, when reacts with alcohol, you will be getting in your conversion questions. So please remember this catalyst, right? Catalytic dehydrogenation process. Now, the next method of preparation of aldehyde ketone is again very important because you get so many questions from this in your exam. But this time it is from alkene. And again, this reaction is a repetition. If you remember your hydrocarbons chapter, so in your hydrocarbons chapter, you talk about ozonolysis of alkene in the chemical reactions of alkene. Now what happens here? When you take alkene, so alkenes are those compounds which have CC double bond, right? So when you take alkene and you treat that with ozone followed by zinc, so it is called reductive ozonolysis more precisely, but sometimes instead of using reductive ozonolysis, we say it ozonolysis. So you need to understand that when I say ozonolysis, so by default it means reductive ozonolysis. So when you do reductive ozonolysis, you will be getting aldehyde as well as ketone depending upon the structure of your substrate. Now, I think for this particular reaction, deciding what products I will be getting is very easy. You know what to do? You have your alkene, you do reductive ozonolysis to get product, just break the double bond and add oxygen on your carbon atom. Point is, when you break the double bond, so for both carbon, right, two valencies are now empty, right? Both of the carbon after fusion of 2 bonds, they can form 2 new bonds. And you know that oxygen creates exactly 2 bonds. So break the double bond and attach oxygen atom on both the carbons. You will get your product. So here from the left part, I will be getting RCH double bond O, which is a aldehyde, and from the right part, right, I will be getting C double bond O H, which is again aldehyde. This is called commonly formaldehyde. So in order to decide what product I am getting for reductive ozonolysis, what I need to do, just break the double bond and attach oxygen atoms on both the carbon between which you have the double bond, right? Like in this case, I am getting 2 aldehyde molecules. Like suppose if I have this kind of compound like RCH double bond C CS3 R dash, right? And for this compound now I am doing the reductive ozonolysis. Now here again, if you notice, you have the double bond. So when you do reductive ozonolysis, here again same approach you can apply. You break the double bond and on both of these carbon attach oxygen by double bond. So here from this left hand part, RCH part, you will be getting what? RCH double bond O, which is an aldehyde, and from the right hand part you will be getting R dash CCS3, R dash C CS3, and this carbon will have the oxygen with double bond. So in this case, if you notice, right, you are getting one molecule of aldehyde and one molecule of ketone. So depending upon what substrate you have, you can get both aldehyde and ketone by the reductive ozonolysis of alkene. Now, one more point. Suppose that in your substrate, if you have more than one double bond, so in that case, you need to do the reductive ozonolysis of all the double bonds. So when more than one double bond is there, break all the double bonds, and same like attach oxygen at all those carbons from where you are breaking the double bond, and you can easily get your product, right? Of course, here we are not talking about the mechanism. It is a direct trick from which you can get the product. And if you check the mechanism, so in your mechanism, you know that by ozonolysis, first we get ozonide, right? And when that ozonide is treated with zinc, then you get your desired product, which is aldehyde or ketone, right? But at least from this trick, you can easily find the product, and that's what you need for your NEET examination. That's what you need for the NEET examination, correct? So now students, can you solve this problem, all of you, quickly? Compound X on reaction with O3, so we have an unknown compound X, which when reacts with O3 followed by zinc gives formaldehyde. So one of the product we are getting is what? Formaldehyde. And formaldehyde is HC double bond OH. And the other product is 2-methyl propanol. If you draw the structure of 2-methyl propanol, so propanol is C double bond O, H, CH, CS3, and 2-methyl means on the second carbon you have a methyl group. So this is nothing but 2-methyl propanol. This is your formaldehyde. And these two are the products you are getting by the ozonolysis of X. Now students, from your alkene, in order to get the product, what you do, you break the double bond and you attach oxygen on both the carbon. Now, here we have to get the substrate from the product. So we can do the reverse task. Here what we can do, from the carbonyl, remove the oxygen. From the carbonyls, remove these oxygens and attach these two carbons with double bond, right? So then you will get your substrate. And in this case, your substrate will be this CH2 attached with double bond by this carbon, which has a hydrogen, and again it has a CH and 2CH3. So this should be your substrate in this case in order to get formaldehyde and 2-methyl propanol. If you check the options, right? So you need to write the name of this compound. I think if you do nomenclature, so this compound has a double bond. So this is your parent chain. Numbering will be done from the left hand side. So 1, 2, 3, 4. The name of the compound should be 3-methyl but 1-ene. 3-methyl but 1-ene. 3-methyl but 1-ene. That means B is your answer. And yes, B is your answer. But this simple question of just finding the substrate, we got in the NEET 2022 examination, and this type of question you can still expect in your examination too. You can expect this in your 2026 examination, right? So now, can we talk about the next method of preparation of aldehyde or ketone? Because again, when you talk about hydration of alkyne, so by the hydration of alkyne, both aldehyde and ketone can be prepared. I hope you know very well what is alkyne, right? Alkynes are those compounds which have carbon-carbon triple bond. Point is, students, if you take alkyl, so I am much more concerned in this CC triple bond. The rest part of carbon chain, I represent it as alkyl group. So you have a triple bond here. That means it is an alkyne. Now when alkyne, they are hydrated, of course hydrated with water. So as compared to alkenes, right, the reactivity of alkynes toward hydration is less. So that's why in order to do the hydration of alkyne, you require some catalyst, which is commonly mercuric sulfate along with acid. When you do hydration of alkene, so there you don't require this mercuric sulfate catalyst. In case of alkene, you just need the water and acid. But in case of alkyne, we need this mercuric sulfate catalyst. Sometimes in your question, it will be simply written like Hg2 plus, Hg2 plus. So point is, here you get Markovnikov product, right? Here you get what? Markovnikov product. So during hydration, the H plus part will be added on this carbon which has one hydrogen, and OH minus part will be added on this carbon which has less hydrogen. So your product will be RCOH double bond CH2. Of course, because we have a triple bond here, so by one time addition, by addition of hydrogen here and OH group here, one of the pi bond will break and you are left with one sigma and one pi. So if you remember, students, this is nothing but enol. This is nothing but enol. Remember tautomerism from the isomerism topic. So here, for this enol, further you will have tautomerism. And what is the meaning of tautomerism? Tautomerism simply means exchange of hydride and pi bond. Like here you have a pi bond between carbon-carbon, and you have a hydride or hydrogen on the oxygen atom. So what will happen? This pi bond will be transferred towards oxygen and this hydrogen will be transferred towards this carbon, right? So after tautomerism, after shifting of this pi bond and hydrogen atom, your final product after tautomerism will be R group, alkyl group, right? Then this carbon, which is having a double bond now with oxygen, and then this carbon will become CH3. So this is nothing but your ketone. This is nothing but your ketone, right? So point is, most of the time by the hydration of alkyne, you will be getting what? Ketone. But if you use ethyne, right? If you use ethyne means CH triple bond CH. In case of ethyne, if you do hydration by the same catalyst, same medium, right? In this case, because we have only two carbon, so one carbon there we will add H, and on the other carbon we will add OH. So your product will be CH OH double bond CH2. And again here by tautomerization, this pi bond will transfer towards oxygen and this hydrogen will transfer towards carbon. So you will end up getting acetaldehyde here. You will end up getting acetaldehyde here, which is aldehyde basically. So point is, by the hydration of ethyne, we can obtain aldehyde. But for the rest of the alkynes, whether it is propyne, butane, pentyne, for the rest of the alkynes, you will be getting what? Ketone. One more point I would like to add here, like if you go into the mechanism of hydration. So according to the mechanism here, with your alkyne, first this Hg2 plus ion will attach like an electrophile, right? So in the mechanism part, you can say that first of all, one of the pi bond of your alkyne, it will share its electron with the mercury ion and you will get a cyclic intermediate like this. You will get a cyclic intermediate like this, right? Cyclic intermediate. And later on, this H2O will work like a nucleophile and then it will attack on this carbon. So this bond will break and later on, this carbon will grab a proton from the medium to convert into CH2 group. So why I'm talking about mechanism here? Because when you do acid catalyzed hydration of alkene, so in that case, you get carbocation intermediate. Now point is, when you do hydration of alkyne, right, in the presence of mercuric sulfate catalyst, so in this case, you don't get any case of carbocation. You don't get carbocation intermediate. So in this case, no rearrangement is possible. Instead of carbocation, we get a cyclic intermediate here, which looks quite similar to the intermediate that you get when you do addition of Br2 CCl4 on alkene, or Br2 water on alkene, or if you talk about oxymercuration, demercuration reaction of alkene. So in those cases, you get this type of cyclic intermediate, right? So here also, in the hydration of alkyne, first we get cyclic intermediate, and then water acts as a nucleophile. It attacks on the higher degree carbon, right? And finally, we get the product, which is strictly according to Markovnikov rule, which is strictly according to Markovnikov rule. So you can say one thing is common between both alkene and alkyne. When you do hydration of alkene alkyne, in both the cases, you get Markovnikov product. That part is common for both alkene and alkyne, right? And again, from ethanol, you can get aldehyde, not from ethanol, sorry, from ethyne, you can get aldehyde group, but from the rest of the alkyne, you can get what? Ketone, right? So, after the preparation of aldehyde ketone from alkynes, now let's talk about some of the name reactions. You know that in this chapter, name reactions are very important. So many name reactions we have in the preparation part itself. So first name reaction we have is a Rosenmund reaction. Now, for name reactions, you need to remember everything, right? What is your substrate, what is your reagent or catalyst, and what product you get. Students, in Rosenmund reaction, what happens? We take acid chloride or acyl chloride as a substrate, right? As your substrate. And you treat that by H2 PD BaSO4. So you can say that it's a kind of partial hydrogenation. It's a kind of partial hydrogenation we have here, right? So now when this acid chloride is treated with H2PD BaSO4, what happens? This chlorine will be removed and your product will be none other than aldehyde, right? So it's a very much direct reaction. We take acid chloride, we treat with H2PD BaSO4, chlorine is removed and we get a hydrogen here. So we get aldehyde as the product. But again, from Rosenmund reaction, you can prepare only aldehyde, you can't prepare ketone. But in the aldehyde, you can prepare both aliphatic as well as aromatic aldehyde, right? If I take a phenyl group here, right? Phenyl COCl. So by the reaction of that benzene COCl, I will get what? Benzaldehyde. So both aliphatic aromatic aldehydes can be formed here, but not ketone from the Rosenmund reaction. And I am again telling you that for every name reaction, you need to remember what is your substrate as well as what is your reagent and catalyst, right? Now, after Rosenmund reaction, let's see some questions from the Rosenmund reaction or the hydration of alkyne that we have discussed. Can you do it by your own? Because it's a very simple question, I guess. The following conversion is known as, so if you notice, in the substrate part, we have acid chloride. Acid chloride is treated with H2BD BaSO4 and we are getting benzaldehyde. So clearly, it is none other than Rosenmund reaction, right? So if you check out the options, no Stephen, no Getterman coach, no Itard, it is none other than Rosenmund reaction. So we got a direct question, right, from this Rosenmund reaction in the NEET 2023 examination. And of course, here your answer is D. Your answer is D because it is a Rosenmund reaction. So now students, the next method of preparation we have is Stephen's reaction. Again, it's a name reaction and it's a very much important for you because we get questions from this, right? And we have got this so many times already in the previous year NEET examinations. So first of all, let's understand what do we mean by Stephen's reactions. Of course, it's a preparation of aldehyde, but Stephen reaction is something like this. You take cyanide or nitrile. I hope you people know about the structure of cyanide or nitrile. Cyanide, nitrile, it has a C triple bond N where nitrogen has the lone pair. And if you talk about the polarity, because you know inorganic, the polarity is very important because that tells you where your electrophile or nucleophile will attack. So in your cyanide, the carbon carries some delta positive charge and nitrogen carries some delta negative charge. Now what do? We do the partial reduction of this cyanide, and partial reduction of this cyanide is done by SnCl2 and HCl. what this SnCl2HCl will do, it will add hydrogen on this carbon nitrogen and one of the pi bond will be removed. So by the partial hydrogenation, or you can say by the partial reduction of this cyanide, we get RCH double bond NH. And this is, students, nothing but it is called imine. This is called imine. You know what? When you have a carbon single bonded nitrogen and nitrogen has some hydrogen, then it is called amine. But when you have a carbon double bonded with nitrogen, then it is called what? Imine. Now, once you have obtained the imine, you simply do the hydrolysis of that imine. So after hydrolysis, what will happen? The nitrogen part will be completely removed one by one, and this carbon will have the oxygen group due to hydrolysis. So after hydrolysis, this C double bond N part will break and you will get RCH double bond O. And I think if you talk about the mechanism here of hydrolysis, so one by one, nitrogen will gain the H plus from water, carbon will gain the OH minus from water. And after fission of this double bond, ultimately this left part will be something like this, RCH, and this carbon will have 2 OH. But you know that generally carbon having 2 OH group, 2 hydroxy group is unstable. So here dehydration will happen. So after dehydration, you will get your C double bond O, right? So by the hydrolysis of this imine, ultimately one side we get this aldehyde and the other side you will get ammonia. Other side, other product will be NH3, right? One more point I should mention here that when you do reduction of cyanide, then you do hydrolysis, you obtain aldehyde. But suppose, students, if you do direct hydrolysis of cyanide in acidic medium, so by the direct hydrolysis of cyanide, you obtain carboxylic acid. So with cyanide, we can get carboxylic acid by the direct acidic hydrolysis. But if you do partial reduction and then you do hydrolysis, you obtain what? Aldehyde. And again, from this Stephan reaction, you can obtain only aldehyde but not ketone. And in aldehyde part, you can obtain both aromatic as well as aliphatic aldehyde, right? But here we have a point. Of course, when I use this reagent SnCl2HCl, right? So then it is called Stephan's reaction. But students, point is, with your cyanide, apart from SnCl2HCl, some other reagents can also be used. So we need to talk about those catalysts, those reagents also. I hope you may have heard about double H. It's very famous. You should know it. Double H, the full form is diisobutyl aluminium hydride. And if you talk about the structure of double H, so it is something like we have aluminium here, hydrogen, then isobutyl and isobutyl. This is the structure of your double H, right? Aluminium with hydrogen and 2 isobutyl. But the main thing is, you should know the function of double H. What double H does? When you treat any substrate with double H, so aluminium will take electron from your substrate, right? Aluminium will take electron from your substrate because aluminium is octet deficient here. And it will give you this H minus ion. It will give you this H minus part, and this H minus you can attach on the atom which has delta positive charge. So overall, you can remember like this, that double H simply helps you in adding H minus ion somewhere. Of course, on that atom which has a delta positive charge, on that atom only you will be adding H minus, because nucleophiles always attack on positive center, right? So point is, if I take that nitrile, if I take that cyanide and I treat that with double H, so what happens? In your cyanide, just now I told you that your nitrogen has some delta negative charge and carbon has some delta positive charge. So when I treat this with double H, right? So in double H, you know the structure. You have your aluminium, you have the isobutyl groups, and you have a hydrogen. So what will happen? Initially, this nitrogen will share its lone pair with your aluminium. So aluminium will gain electron from the nitrogen atom. And because this carbon has a positive center, the carbon has some delta positive charge, this aluminium will release this H as H minus, and this H minus part, it will attach on this carbon. So it will give you an addition product, something like this, R, C, H, double bond, N, and this N is now attached with your aluminium, which carries isobutyl group. So double H first, it gets added on your substrate, right? Aluminium and hydrogen. Aluminium is added in this case on nitrogen because nitrogen was electron rich, and hydrogen was added on this carbon because carbon has delta positive charge. But as soon as you do hydrolysis, when you do hydrolysis here, so after hydrolysis, this bond, this double bond, C double bond N will break, just like the imine case, remember, in the Stephens reaction, right? After reduction of cyanide into imine, when we did hydrolysis of imine, we got a carbonyl group. So similarly, when you do hydrolysis of this C double bond N, oxygen will come and you will get aldehyde. So point is, not only by Stephens reaction, not only by SnCl to HCl, right? But also with help of double H, we can obtain aldehyde using cyanide. So double H and cyanide combination, right, followed by hydrolysis, can also give you aldehyde. But your task is to remember the reagent double H. Remember that double H is Al isobutyl hydrogen, and first it always gets added on your substrate. Aluminium will be added on that atom which has electron richness, which is rich in electron, which has negative charge, and hydrogen will be added, hydride will be added, H minus will be added on that carbon which has delta positive charge. And then if you do hydrolysis, you can obtain different product. In this case, we got aldehyde, right? So double H is very important, and double H you should always remember with your Stephens reaction. Whenever you revise the Stephens reaction, so along with the Stephens reaction, you should also revise the double H reagent. Now, if you talk about the next preparation, that is from ester, how we can obtain aldehyde. So here also, you will be using double H. Students, you know very well that ester group looks like this. You have alkyl group, carbon chain, right? Then carbonyl, and then you have this alkoxide, OR dash. So when you take ester, and if you treat ester with double H, so just now in the previous mechanism, you saw that double H can provide you with H minus, right? So here what the double H will do, you have your aluminium, hydrogen, isobutyl, right? Now you understand very well that here aluminium will try to take electron from your substrate. And in your substrate, this oxygen atom has lone pair, right? So this oxygen will give lone pair to the aluminium atom. Now here this hydride will be getting added to this carbon, which has positive charge, and this bond will break. So ultimately, when you treat ester with double H, aluminium takes the oxygen, the alkoxide group, and hydride gets added on the carbonyl, and your product is aldehyde. So point is, students, when we treat ester with double H, directly we obtain aldehyde, right? So from ester also, you can prepare aldehyde using double H, right? Now, can you answer this question quickly, all of you, by your own? Identify the suitable reagent for the following conversion. And if you look at the conversion, it is very much known to you now, isn't it? Can you see this? Benzene, carbonyl, OCS3, this is nothing but ester. And here this ester is getting converted into benzene CHO, benzaldehyde. So what we are doing, we are converting this ester group into aldehyde group. And just now you saw that ester can be converted to aldehyde directly using double H or diisobutyl aluminium hydride. Now if you look at the options, in the first option we have NaBH4, which is a mild reducing agent, and NaBH4 cannot reduce ester. So A is not at all possible. Then if you talk about H2PD, BSO4, this also cannot reduce ester. Now if you talk about LiAlH4, so LiAlH4 is quite stronger than NaBH4. So LiAlH4 will react with ester, but it will give you alcohol. Lithium aluminium hydride, when it reduces ester, it can give you what? Alcohol. But here your product is what? Aldehyde. So definitely in this case, in option D we have right? ALH isobutyl twice. This is nothing but double H. This is nothing but double H. So if you treat with double H water, the ester can be directly converted into aldehyde. So of course, in this case, the answer will be D. And this question of double H, we got directly in the NEET 2025 examination. So now you can understand that those reducing oxidizing agents like PCC, Jones reagent, LiAlH4, NaBH4, double H, these 4 or 5 reagents are very much important for you. You get a question from this so many times in your exam, right? Now, can we talk about the next preparation of aldehyde again, which is a name reaction, Itard reaction, very much famous. In Itard reaction, what you do, you convert toluene directly into benzaldehyde, right? In Itard reaction, your substrate is toluene, benzene, CH3. And when you treat this benzene CH3, methyl benzene, or commonly called as toluene, when you treat this toluene with chromyl chloride, so chromyl chloride is your reagent here, right? And for this reaction, at least, you should have the knowledge of structure of chromyl chloride, CrO2Cl2. The structure of CrO2Cl2 is something like this. You have your chromium, and the two oxygens, they are bonded by double bond. And the two chlorines, they are bonded by single bond. So this is the structure of chromyl chloride. Now, when you treat methyl benzene with CrO2Cl2, first you get an addition product. What happens to students? Please notice here. The chromyl chloride kind of functions like an oxidizing agent. The chromyl chloride, because this chromium has oxidation number of +6, so it tries to take electrons from your substrate. And from your substrate, if you compare, the electron which can be most easily donated is the electrons of your CH bond here. These electrons can be easily given to your oxidizing agent. So what happens? This electron of CH bond, it is shared by the chromium, right? And when this electron pair will be shared by the chromium, one of the pi bond between chromium oxygen, it will break. And ultimately this O will get negative charge. You know very well that when this pi bond will shift on oxygen, right, O will get negative charge. And this O negative will take this H plus, right, to give you this kind of structure, benzene, carbon. Now this CH bond is given to CrO2Cl2. So this CrO2Cl2 will be added with your carbon, something like this, Cr. This double bond will be as it is. This single bond will be as it is. And this double bond will be converted into OH, right? Now, the same thing will happen 2 times, right? One more time, one more CrO2Cl2 will take electron from another CH bond, right? And you get you will be getting same type of structure, right? Another chromine, double bond O, OH, Cl, Cl. But one of the CH bond will be preserved here. Why? Because after addition of 2 chromyl chloride, after addition of 2 molecules of chromyl chloride, now this carbon, if you notice, it has 3 bulky groups. 1, this, 2, phenyl, 3, this. And you know very well, even from your SN1, SN2 reactions and all, that when a carbon has 3 bulky groups, so it has a high steric hindrance. So because of high steric hindrance, one of the CH bond will be preserved here, right? And ultimately, you will get this addition product when your toluene is treated with CrO2Cl2. But when we get this addition product, what we do hydrolysis further, right? And when we do hydrolysis, then these carbon chromium bonds, they will break one by one. Like water will act as a nucleophile here. When water will attack on this carbon, these electrons will be taken by chromium, both sides. One more water molecule will be there. So it will also attack on this carbon. So this electron pair will be taken by chromium. So during hydrolysis, the H2O molecules will attack on the carbon, and these chromiums, they will take away the electron. And ultimately, on the carbon, you will have 2 OH group. Now in the previous reactions also you saw that when a carbon has 2 OH group, so we have dehydration there, and ultimately carbon having 2 OH groups, it converts into carbonyl group. So ultimately, in this case, after hydrolysis, the product we get is carbon having this hydrogen and double bond O, which is nothing but benzaldehyde. So toluene, right, when it is treated with chromyl chloride followed by hydrolysis, gives you what? Benzaldehyde. And this particular reaction is called as Itard reaction. Now, one more point I would like to add here. Using chromyl chloride followed by hydrolysis, we can convert toluene into benzaldehyde. But one more method is there by which you can convert this toluene into benzaldehyde, right? And that is using CrO3 and acetic acid, right? Instead of chromyl chloride, if you use CrO3, right, in acetic acid medium, so by that also you can convert toluene into benzaldehyde. But toluene by chromyl chloride followed by hydrolysis, this reaction is called as Itard reaction, and it is again very much important for you for your examinations, correct? So can you solve these questions now? Can you solve this question now, all of you, by your own? Because just now we discussed Itard reaction. The intermediate compound X in the following chemical reaction. Now, if you notice, this is nothing but Itard reaction, right? Methyl benzene treated by CrO2Cl2 followed by hydrolysis, we are getting what? Benzaldehyde. So they are asking about this X. So I told you that two molecules of this CrO2Cl2, it will be added on this carbon, and one of the hydrogen will be preserved, and that will be your intermediate. Now if you check the options, chlorine, no. Chlorine hydrogen, no. Now third one, the carbon has one hydrogen and the rest two are CrOOH Cl2, right? So of course here the answer should be third one. Answer should be third one, right? And this question from Itard reaction again we got in the NEET 2021 examination. One more point. If you check the fourth option, of course fourth is not the answer here, but if you check the fourth option where we have carbon having a hydrogen and two acetate groups here. So this intermediate we do not get in Itard reaction, but this intermediate we get when we treat toluene with CrO3 and CH3COH, right? And by the hydrolysis of this also we can obtain benzaldehyde, right? So I hope you are getting this, that this intermediate we get when we treat toluene with this reagent CrO3 CH3COH. But with chromyl chloride you will be getting this intermediate CHO CrOH Cl2 whole twice, correct? Of course the answer of this question is third. And now let's talk about few more preparation of aldehyde itself, right? This is very easy one, by side chain chlorination. I hope in your alkane chapter you must have seen free radical halogenation, free radical chlorination, free radical bromination. So using free radical chlorination or bromination also we can prepare aldehyde, right? How? It's very easy. You take a benzene having side chain means like this, methyl group. Now for this compound, if I do chlorination, free radical chlorination, more precisely dichlorination, if I do dichlorination, two equivalents. So if you do dichlorination, two of the CH bond will break and on carbon 2 chlorine will be added, right? So one by one, this is the sp3 carbon, and you know that sp3 carbon is preferred over sp2 in free radical chlorination or bromination. So on this sp3 carbon, when you do dichlorination, the two CH bond, they will break, and on your carbon now, instead of hydrogen, you will have chlorines, right? So by double chlorination, the product will be something like this, carbon having a hydrogen and two hydrogens, they are now replaced by the chlorine group. Now, for this compound, if you simply do hydrolysis in basic medium, right? So during hydrolysis, SN reaction will happen, right? The OH minus group, one by one, they can replace the chlorine. The OH minus group, they can replace the chlorine. And you know very well that when 2 chlorine will go out, on carbon 2 OH will be there, but on carbon 2 OH is generally unstable. So again, carbon having 2 OH, it will go through dehydration, and carbon having 2 OH, it will convert into carbonyl. So ultimately, here also the product will be carbon having a hydrogen and double bonded oxygen. This is nothing but benzaldehyde. So just like ETARD reaction, right? In side chain chlorination followed by hydrolysis also, you can convert your toluene into benzaldehyde. So this is another method we have for the preparation of aldehyde. Now, talking about a question here, I think this question now you can do very well. I hope so. And if you want, you can answer this question in the comment box. I will check the comments, right? Whether you are right or wrong. So pause it, do it by your own first, then later on you can check your answer. Question is, identify compound X in the following sequence of reaction. So what's the sequence? Sequence is, we have methyl benzene, we are doing chlorination. So by chlorination we are getting some X, and for this X when we are doing hydrolysis, right, we are getting this as aldehyde group. Now just now we saw that not by monochlorination. If you do monochlorination, then if you do hydrolysis, you end up getting alcohol. But by dichlorination, we get this product, and hydrolysis of this dichloro compound, right, gives you what? Aldehyde. So now if you check out the options, CH2Cl not possible because hydrolysis of CH2Cl will give you CH2OH. CHCl2 yes, CCl3 not possible because CCl3 we get by trichlorination, and if you do hydrolysis of CCl3 you get carboxylic acid group, not aldehyde. And C, this is not at all possible. So in this case, the only possible option is CHCl2, option B, right? Because by the hydrolysis of this dichlorinated product, we get aldehyde. And this question, students, again, we got in NEET 2020 examination. Correct? So now you can guess what type of questions you get in the NEET examination. Now we have another very famous name reaction for the preparation of benzaldehyde. Yes, from Getterman-Koch reaction, we do prepare what? Benzaldehyde. And it's a very neat and clean reaction. You can also say that Getterman-Koch reaction is one of the examples of electrophilic substitution reaction of benzene. Of course, you don't discuss of this reaction in your hydrocarbon chapter. We talk about this here only, but Getterman-Koch is an example of electrophilic substitution reaction. Now, you know what happens in this reaction? You take benzene and you treat benzene with reagent carbon monoxide and HCl. Carbon monoxide and HCl. And in this reaction, we will have catalyst like AlCl3, anhydrous of course, or copper chloride, CuCl. So AlCl3 or CuCl will function like a catalyst here, and COHCl is your reagent. Of course, in this case, the product will be directly benzaldehyde, but let's see what happens exactly in this reaction. See, if you talk about HCl, so HCl, it is ionic, right? In the presence of AlCl3, I hope you know that AlCl3 is Lewis acid. Lewis acids like AlCl3, CuCl, right, Cu2Cl2, Fe, FeBr3, FeCl3, they always attract the nucleophile part. So in your HCl, when it will interact with AlCl3, it will attract the chloride, and it will release the H plus ion. So chloride will combine with AlCl3 to give you AlCl4 minus, right? Now this H plus will interact with your carbon monoxide molecule, and if you know your carbon monoxide, so it has a bond order of 3, carbon has a lone pair, oxygen has a lone pair, but they do have formal charges also. O has plus charge, C has minus charge, right? Now this H plus, when it will interact with this CO molecule, of course oxygen has positive charge, carbon has negative charge, so H plus will be added on this carbon, right? So this carbon will share its one of the lone pair with H plus, right? And simultaneously, the pi bond between carbon oxygen will shift on oxygen in order to neutralize your oxygen atom. So you will be getting this kind of intermediate, carbon attached with hydrogen. Now the triple bond will become double bond. Oxygen from positive charge, it will become neutral because it has gained the pi bond. And the carbon, it will have now positive charge. It is nothing but a carbocation. So this carbocation, now it will act like an electrophile, and this electrophile will react with your benzene. It will have the electrophilic substitution reaction. I hope you people know the electrophilic substitutions mechanism, right? From your benzene, one of the pi bond will be shared by the carbon, right? Arenium ion will be formed, later on hyperconjugation. And simply this electrophile will be substituted on benzene by replacing the H plus ion from the benzene. So your product will be ultimately benzaldehyde. But one thing you need to understand in this reaction is this COHCl along with this AlCl3 catalyst, right, together they generate this intermediate C double bond OH, which acts as an electrophile, and it reacts with benzene to give you the benzaldehyde. And overall this reaction is called as what? Getterman-Koch reaction. Getterman-Koch reaction. Now after Getterman-Koch reaction, now we have, now till now you saw preparation of both aldehyde ketone, but some of the name reactions were there like Rosenmund, Stephens, Itard, Getterman-Koch. So in these name reactions, if you notice, you will be able to prepare only aldehyde. So because from these 3-4 name reactions we can prepare only aldehyde. So separately we have some methods which focuses mainly on the preparation of ketone, right? Mainly focuses on the preparation of ketone. And one of them is reaction of acid chloride with Grignard reagent. I hope you know that Grignard reagent is very much important for you, for your organic chemistry. Grignard is RMgX, and always please remember that Grignard breaks into R minus and Mg plus. Now here, most of the time we directly don't treat acid chloride with Grignard reagent. What we do, we take Grignard reagent, we take the Grignard reagent, and we treat that by cadmium chloride. Cadmium chloride. So from the Grignard, the alkyl group, it will substitute the chloride group from this CdCl2 and it will create dialkyl cadmium. Basically, two molecules of this Grignard will react with one molecule of CdCl2, and from the CdCl2 chlorine will be replaced by the alkyl group. So ultimately you will be getting R2CD. This is nothing but dialkyl cadmium, and the MgX part, it will combine with chlorine. So you will be getting 2 of the MgXCl, right? Now this dialkyl cadmium, it is treated by acid chloride. You know very well acid chloride. Let me say R dash here, just to make a difference. So this is your acid chloride, R dash COCl. And now if you treat this acid chloride with your dialkyl cadmium, right? So from this dialkyl cadmium, what you can get? Of course, you can get R minus nucleophile. So from this R2CD, whatever R minus, whatever alkyl group you get, it will attack on this carbon, right? Liberating the chloride, and ultimately you get what? Ketone. You get what? Ketone. So this is a separate method by which you can prepare only ketone, not aldehyde, right? From acid chloride and dialkyl cadmium, you can prepare what? Ketone, right? These are general reactions. I am not taking example. You can understand that here, instead of this R dash, you can have methyl, ethyl, propyl, phenyl, anything. Anything. Alkyl or aryl groups can be there. And here also, in the R2 part, in the alkyl part, you can have methyl, ethyl, propyl, phenyl, anything. Alkyl or aryl group, right? So from this acid chloride and Grignard, or more precisely from dialkyl cadmium, we can prepare what? Ketone. Now for ketone, one more method of preparation is there, which is nitrile. Previously we saw that from nitrile how we can prepare aldehyde, by Stephens reaction or by treating nitrile or cyanide with double H. Now if you take the same nitrile, this time let me take an example, right? Let's say I have this C2H5 CN. This is your nitrile. So if you take your nitrile, of course nitrile, you know the polarity, carbon has delta plus charge, nitrogen has delta minus charge. And if you treat that with some Grignard reagent, for Grignard, let me take CS3MgBr. CS3MgBr, for example. You know that it will break into Mg plus and CS3 minus. Now if you check the polarity, from the Grignard, the anion part will attack on this carbon and the cation part will join with your nitrogen, right? So it's a kind of addition reaction. It's a kind of nucleophilic addition reaction, because first this C minus will attack on this carbon, then this pi bond between carbon nitrogen, it will break, it will go on to the nitrogen, and nitrogen will take up your Mg plus part. So after the addition of Grignard on nitrile, on cyanide, your addition product will be C2H5, C. Now on C you have a CS3 group, then double bond, N, and with your N, now you have the MgBr part, right? Now ultimately, you have seen many times now in the preparation that whenever we have C double bond N, so by the hydrolysis of C double bond N, ultimately we get C double bond O. So for this product, if you do hydrolysis, right? So after hydrolysis, you can obtain C2H5, C double bond O, CS3, which is nothing but methyl-ethyl ketone. So using nitrile with Grignard reagent also, we can prepare ketone instead of aldehyde, right? Now, a very famous reaction, I think this reaction you know from your hydrocarbon chapter itself, right? Remember Friedel-Crafts alkylation, Friedel-Crafts acylation, right? And the Friedel-Crafts catalyst is nothing but your anhydrous AlCl3. So point is, students, using the Friedel-Crafts acylation reaction, we can prepare ketone. How? If you take benzene, right, and you treat that with acyl group, something like CS3, COCl, in the presence of anhydrous AlCl3 catalyst. So I hope you know what happens here exactly, right? AlCl3, the Lewis acid, it will break the carbon-chlorine bond, right? The AlCl3 will take the Cl minus part and it will create CS3CO plus. It will create CS3CO plus, right? And this carbocation, now later on, it will react with your benzene. It will go through again electrophilic substitution reaction, and your product will be benzene, C double bond O, CS3. If you remember, this compound commonly it is called as acetophenone, right? And just like this, you can keep different alkyl groups here, and you can obtain different alkyl phenyl ketones using Friedel-Crafts acylation, right? So Friedel-Crafts acylation, nitrile with Grignard, and acid chloride with dialkyl cadmium or Grignard reagent. These are some of the reactions from which you can prepare ketone only, not aldehyde, right? So now, let's do few more questions from the preparation of this aldehyde ketone, correct? Can you do this matching all of you by your own? In the left hand side, you have some reactions in which reagent is not mentioned, only substrates and products are given. And in the list 2, you have your reagents or catalyst, right? So if you notice one by one, in the very first option, the substrate is changing into this. So basically, this double bond is having fission and this carbon is getting attached to oxygen. So remember, when you break CC double bond and you attach oxygen both side on both carbon, so that is nothing but reductive ozonolysis. So for this substrate, if I do reductive ozonolysis, it will break into two parts and both part will be ketone. So A should match with the reagent we use in reductive ozonolysis, which is given in option 4, right? So here A will matched with 4, right? Now second one. In second case, we have benzene and it is converting into benzophenone, right? Now here if you look at the options, so in the first option, you have acid chloride in which we have a phenyl ring and anhydrous AlCl3. So this reagent is nothing but for Friedel-Crafts acylation. If you do Friedel-Crafts acylation of benzene, this Cl will go out and this whole part will be attached to benzene. So benzene, CO benzene, you get benzophenone. So basically, B is nothing but, the reaction B is nothing but Friedel-Crafts acylation. So B should match with first here. Now look at the C option. In C option, you have an alcohol which is basically 2 degree. And 2 degree alcohol by oxidation, it will definitely give you ketone. Now if you check out the options, right? So you have CrO3 here. So definitely C can match with CrO3. So that means what? C will be matched with 2. And if you check out D, So in D you have a alkyl group here, and this carbon is directly converted into carboxylic acid group. So a carbon will be directly converted to carboxylic acid, or a side alkyl group will be directly converted into carboxylic acid only by strong oxidation. And strong oxidizing agent we have here in the KMNO4 part, third one, right? So D will match with third. So your answer should be A4B1C2D3. A4B1C2D3. That's your answer, right? So it's a direct question, but overall concepts of all the preparations are used here. And this question we got in the NEET 2024 examination. Now, can you do this one? It's not only from aldehyde ketone chapter, it is from rest of the chapters too. But this ITAD reaction is there. That's why I have included this question in this session. So again, you have a matching here, but it's very much direct. If you remember, all of these are name reactions, right? Gabriel synthesis or Gabriel thalamide synthesis. You must have seen in the amine chapter, right? It is used for the preparation of primary amines. So here, A will be matched with third. And second, coal-base reaction or coal-base synthesis, you must have seen that in the phenol chapter. So when phenol goes through coal-base synthesis, it gives you salicylic acid. So B will be matched with fourth one. Now Williamson synthesis, it's very famous. It is used for the preparation of ether. So C here, it will be matched with second, ether. And ITAD reaction, today only we saw ITAD reaction, that ITAD reaction converts toluene into benzaldehyde. So D will be matched with first. So answer should be A3B4, A3B4, C2 and D1. That means option A. And yes, option A is your answer. I hope that most of you have done this question by your own, right? And this question, students, we got in the NEET 2022 examination, correct? Now, can we do one more? The incorrect method to synthesize benzaldehyde. So we have four methods here. And out of this, one method is there which can't give you benzaldehyde, which can't give you benzaldehyde. If you check out the first option, so in the first option we have acid chloride, treatment with H2PDBaSO4. So if you remember, when you treat acid chloride with H2PDBaSO4, this chlorine will be removed by hydrogen. You get benzaldehyde from this, and this is none other than your Rosenmund reaction. This is your Rosenmund reaction. So first will give you benzaldehyde. If you check the second one, so you have ester in second, and ester treated with double H followed by hydrolysis. Double H can give you H minus, that H minus can replace this ethoxide. So even this can give you benzaldehyde. If you check the third option, so in the third option you have a toluene, methylbenzene, treated by CrO2Cl2 followed by hydrolysis. Now if you remember, when we treat methylbenzene with chromyl chloride followed by hydrolysis, this is none other than your ITAD reaction, right? And with your ITAD reaction also you prepare benzaldehyde. So even from third also we can get benzaldehyde. Now if you check the fourth one, yeah, if you treat nitrile with Grignard or dialkyl cadmium, any of these two, right? If you treat nitrile with dialkyl cadmium or Grignard, it will give you ketone, not aldehyde. Like in this case, when I treat CN with CH3 MgBr, first this CH3 minus will attack on carbon, right? N will be added to Mg plus Br. And if you do hydrolysis later on, the product will be benzene, C double bond O, CH3, acetophenol. So here fourth will be your answer, because from the fourth case you are not getting benzaldehyde, you are getting acetophenol. Yes, answer is fourth. And this question, students, we got in NEET 2022. So you must have been noticing that in each and every session, I try to cover as much as PYQ I can. Because from PYQ you can relate, right, what type of questions you get in your exam. So now students, after the preparation of aldehyde and ketone, the next point is, like when you talk about the properties of aldehyde ketone, like before we begin with chemical reactions of aldehyde ketone, we need to see regarding the boiling point and solubility of aldehyde ketone. Point is, you know very well what is boiling point, the temperature at which your liquid starts converting into vapor, right? So if you compare the boiling point of aldehyde ketone, if you compare the boiling point of aldehyde and ketone, right? So aldehyde ketone, they have van der Waals force, and more precisely they have the van der Waals force which is a dipole-dipole interaction because they have polar carbonyl group. So because of polar carbonyl group, they have a weak van der Waals force which is basically dipole-dipole force. But if you compare aldehyde ketone with corresponding hydrocarbons, right, or ether, so as compared to hydrocarbons and ether, if they have nearly same molecular mass, if they have nearly same molar mass, so of nearly same molar mass, hydrocarbon ethers, right, they will have low boiling point as compared to aldehyde ketone, right? But aldehyde ketones, they will have low boiling point as compared to corresponding alcohols, because you know that in alcohol we have an intermolecular hydrogen bond, but aldehyde ketone, they lag in the intermolecular hydrogen bond. So aldehyde ketones do have a higher boiling point than hydrocarbons and ether, but they have less boiling point as compared to alcohol or carboxylic acid. Also, you need to remember some of the points, like if you talk about methanol, the first member of your aldehyde group. So methanol is a gas at normal temperature. If you talk about ethanol, so ethanol is liquid, but it is moreover volatile liquid, and the rest members or the higher members of your aldehyde ketone groups, they are like either liquid or solid, right? But at least these two, methanol and ethanol, you should remember, right? And you know, few points like boiling point decreases by branching. Those things you know from your previous chapters also, that boiling point increases with molar mass and decreases with branching, right? Those parts also can be asked in the examination. And talking about the solubility, right? So solubility of these organic compounds in water mostly depends on the ability to form hydrogen bond, right? Now, definitely, carbonyl group, they do have an ability to form hydrogen bond, because in H2O molecule you have H plus ion, and in carbonyl you have this O negative ion, right? So this carbonyl or the oxygen of carbonyl can form a hydrogen bond with hydrogen of water, but still, when your alkyl groups are smaller here, smaller here, so in that case they are partially miscible with water, right? But when your alkyl groups are bulky, or if your number of carbon in your alkyl group increases, so with increase in number of carbon in the alkyl group, the solubility of both aldehyde ketone will decrease. So you can say like this, that lower members of aldehyde ketone, they are miscible in water, but the higher members of aldehyde ketones, they are not soluble in water, right? And the solubility decreases here by the increase in alkyl group, by the increase in number of carbon in the alkyl group. So sometimes you do get questions from the boiling point and solubility point of the aldehyde ketone, right? Like just check out this question, all of you, carefully. Can you do it by your own? We have two statements and we have to answer that which statements are correct here and which statements are incorrect. First statement is the boiling point of aldehyde ketones are higher than hydrocarbons of comparable molecular mass. Definitely. Just now I told you that boiling point of aldehyde ketone is higher not only than the hydrocarbon but also than the ether, right? Why? Because aldehyde ketone, they have a dipole-dipole interaction. On the other side, if you talk about hydrocarbons, so hydrocarbons, they have induced dipole attraction, London dispersion forces, right? And induced dipole is weak as compared to dipole-dipole. So here statement 1 is absolutely correct. And if you talk about statement 2, the boiling point of aldehyde ketone are lower than the corresponding alcohol of similar molecular mass due to absence of hydrogen bonding. We know this point also, right? That because alcohol have intermolecular hydrogen bond and aldehyde ketones, they do not form intermolecular hydrogen bond. That's why alcohols will have a more boiling point as compared to aldehyde ketone of comparable molecular mass. So even the statement 2 is correct. So here your answer should be statement 1 is incorrect. No. Both statement 1 and statement 2 is correct. Yeah, so answer should be B here. So point is, sometimes you do get question from these points like boiling point and solubility. And this question we got in the NEET 2022 examination. Now, after this boiling point and solubility, we will start with the chemical reactions of your aldehyde ketone. But before we begin with the reactions of aldehyde ketone, first you need to understand very well the structure of carbonyl. Students, please see carefully. You know carbonyl group very well. In carbonyl you have carbon doubly bonded oxygen, and here on one side if you have alkyl group and other side if you have hydrogen, so that is your aldehyde, and on both side of this carbon if you have alkyl group, so that is your ketone. Correct? But both aldehyde ketone, they have this point, they have this part, C double bond O. Now in the C double bond O bond, in the C double bond O bond, if you notice, out of carbon oxygen, definitely carbon is less electronegative and oxygen is more electronegative. So if you check the polarity of this bond, polarity of this double bond, your oxygen atom will have always some delta negative charge because it is more electronegative, and your carbon atom will have always some delta positive charge because carbon is less electronegative. Now, why we are talking about the structure or polarity of carbonyl group? Because that will help you in your reactions. So from this polarity, you can guess one thing. What? Whenever a negative species, an ion or nucleophile, is going to react with the carbonyl group, so negative ion or any nucleophile part, it will always attach with your carbon atom. And at the same time, if there is a particle having positive charge, or which you often call as electrophile, so electrophiles in the carbonyl, they will always try to attach with the oxygen. So by knowing the polarity of carbonyl group, you can easily decide that out of the nucleophiles or electrophiles, which can attack where. Right? In carbonyl, nucleophiles will always attack on carbon, and electrophiles will be always added on the oxygen atom of the carbonyl. Right? So after knowing the polarity of carbonyl group, now let's begin with the very first reaction of aldehyde ketone, which is again very famous. It is nucleophilic addition reaction. I think in your hydrocarbon, when you talk about alkenes, so for alkenes or alkynes, you study electrophilic addition reaction. Now, during electrophilic addition reaction, what happens? From your alkene, first electrophile will be added, and later on nucleophile will be added. Now here, the thing is reversed, right? When you react aldehyde ketone with certain reagent, what happens? With aldehyde ketone, first the nucleophilic part will react. First the nucleophile will react. Later on the electrophile part will be also added, but because first nucleophile is getting added, so we call these reactions as nucleophilic addition reaction. Now first let me tell you a general scenario of the reaction. What happens here? You take any carbonyl here, it means aldehyde ketone, not the rest ones, not the carboxylic acid, not the amide and all. Here, if you take aldehyde or ketone, right, and you react aldehyde ketone with a reagent which can give you nucleophile. So what happens? The nucleophile will attack on the carbon atom. Why? Because the carbon has delta positive charge. And as soon as your nucleophile attacks on the carbon atom, the pi bond of this C double bond O will delocalize onto oxygen, right? And you will get addition product like this. Of course, this O minus later on, it can grab some electrophile to neutralize itself. But this is the general concept of nucleophilic addition. You give any nucleophile to carbonyl aldehyde ketone, the nucleophile will be added on the carbon atom, right? And electrophile later on, it will attach with the oxygen atom. Now point is, inside this nucleophilic addition reaction, we have so many examples, so many compounds can be there, so many reagents can be there from which you can get a nucleophile. Like for example, if I use HCN, so HCN can give you CN minus nucleophile, right? So CN minus can attach with carbon, and H plus can attach with oxygen. Similarly, if you use NH3 ammonia, so from NH3, the nitrogen can attach on the carbon, right? And one of the H plus from NH3 will attach on oxygen, right? If you talk about NaHSO3, right? So from this NaHSO3, the HSO3 minus part, it can attack on carbon, and the H plus part can attach on the oxygen. So we have so many examples of nucleophilic addition, right? In which different nucleophiles will be added. Similarly, you can have addition of alcohol, right? if you react any aldehyde ketone with alcohol, then this alkoxide part will act as nucleophile. Alkoxide will add on carbon, and this H plus will go on oxygen, right? Even you can have addition of Grignard reagent here, right? Because Grignard can give you the R minus nucleophile. So if you treat any aldehyde ketone with Grignard, so that R minus part will attack on carbon and Mg plus part will attach on oxygen. So you give any reagent to aldehyde ketone if it has nucleophile and electrophile. So nucleophile will be added on carbon and electrophile will be added on oxygen. That's the point, right? Now, let's see some of the examples of nucleophilic addition here with help of certain questions, right? Or if you want, I can give you some examples here. I can tell you certain reactions here. See, like if you take aldehyde and let's suppose if you react it with HCl, hydrogen cyanide. So hydrogen cyanide, because it is a weak acid, so to make it more dissociate, right? To dissociate more the HCl, we use certain traces of base in this reaction. Base will help to in the ionization of HCl. So HCl will ionize into H plus and Cn minus. But if you talk about the product here, so product can be easily determined, like Cn minus will attack here, pi bond will go into oxygen, and your product will be R, C, H, Cn, OH. Now point is, why I am writing these examples, because certain names are there which you need to know. Like on your carbon, when you have cyanide and OH group, so this structure is called cyanohydrine. So cyanohydrine will be formed in this reaction, right? Similarly, if you talk about reaction of any aldehyde ketone or carbonyl with alcohol, right? So again, mechanism will be same. In this case, in case of alcohol, you know that oxygen always tries to donate electron. So oxygen will donate electron to the carbon, pi bond will shift onto oxygen, and this H plus will go on this oxygen to give you the product like R, C, H, OR and OH. Now students, from this aldehyde, when you get this structure, that means one of the carbon has alkoxide group and hydroxy group. So this is called hemiacetal. This is called hemiacetal. Hemiacetal. And if you treat this compound, hemiacetal, further with excess of alcohol, so then this OH will be removed and another alkoxide will come here. So this is called as acetal. This is called as acetal. So from aldehyde, by the reaction of alcohol, you can obtain hemiacetal, in which you have hydroxy alkoxy group, and acetal, in which both are alkoxy groups. Similarly, if you take ketone here, so in case of ketone, you get hemiketal and ketal. Hemiketal and ketal, right? And just like alcohol, further if you talk about one more nucleophilic addition of aldehyde ketone, every time I am taking aldehyde, so let's take something different in this. Let's take ketone here, right? Because ketones will also react in the similar fashion. So if you react ketone with, let's say ammonia, right? So in this case, nitrogen will attack on the carbon. Again, pi bond will shift on oxygen. You will get addition product first, like R, C, R, OH and NH2. But please remember one thing, students. Here is a point. Whenever ammonia or derivative of ammonia, like ammonia is there, NH3, and derivatives of ammonia like hydrazine and all, any compound in which your nitrogen atom is there, which is acting like a nucleophile. So if you take ammonia or derivative of ammonia, so in this case, you will have nucleophilic addition. Nitrogen will add on carbon, and on carbon you will get a hydroxy group. But in this case, please remember that you will have always auto dehydration. After addition reaction, after nucleophilic addition reaction, if your nitrogen has hydrogen, so in these cases, automatically there will be dehydration reaction. No requirement of heat is there. Without giving heat also, automatically there will be dehydration. So after dehydration, what will happen? From the carbon OH and from the nitrogen H plus will be removed, and after dehydration it will form amine. It will give you RCH double bond NH. So this point you need to keep in your mind, that whenever ammonia or its derivative reacts with aldehyde ketone, so first you have nucleophilic addition and later on you have dehydration there, right? And similarly, you can now do the addition of Grignard, right? When you do addition of Grignard, so in that case, what will happen? You will have your aldehyde or ketone, right? And Grignards will be added again. This R minus will attack on carbon, pi bond will go on to oxygen, oxygen will bind with Mg plus. And later on, if you do protonation, you can obtain alcohol from this, right? So these are some of the examples of your nucleophilic addition reaction. But in nucleophilic addition reaction, please remember one more thing, that apart from reactions, sometimes you can get questions from the comparison of reactivity of both aldehyde and ketone towards nucleophilic addition reaction. So point is, reactivity of aldehyde ketone towards nucleophilic addition reaction, can be decided on the basis of two factors, right? The major factor is steric hindrance. The major factor is steric hindrance. Means what? If you have bulky groups around your carbonyl, so if you have bulky groups around your carbonyl, then your carbonyl will be less reactive towards the nucleophile. Like for example, if I take aldehyde, and I compare any aldehyde with any ketone, so point is, in aldehyde, one side we have always hydrogen, which is very small in size. But in ketone, both side we have alkyl group, both side we have carbon. So one thing is for sure, that aldehyde has always lower steric hindrance around carbonyl because it has hydrogen as compared to ketone. So because aldehyde has less hindrance, that means what? Aldehydes are always more reactive as compared to ketone towards nucleophilic addition reaction, right? And apart from steric hindrance, the second factor we have from which we can compare the reactivity is electron density. Electron density of carbonyl group. Electron density of the carbonyl group. If your carbonyl group has a high electron density, then the upcoming nucleophile will feel certain repulsion, right? If your carbonyl is electron rich, nucleophile is also electron rich, so they will try to repel each other. So point is, if carbonyls have high electron density, then its reactivity will be less. And if the carbonyl has less electron density, then its reactivity will be more, right? Like let me give you an example here. Suppose if I compare CS3CHO with this compound. Can you see this? In the second case, I have attached a nitro group, which is a -I group here. So what this -I group will do, it will attract electrons from the carbon. So then this carbon will become electron deficient. So this carbon will again try to attract electron of this CC bond. And when this CC bond electrons, they will try to go towards the left carbon, this carbonyl have low electron density. Now this thing is not happening here. In the CS3, the CS3 will show only the +I effect. So clearly in the second case, carbonyl has low electron density because of presence of this nitro group. So second one is more reactive, because if electron density of carbonyl is low, then it is more reactive towards nucleophile. I hope you will remember these two factors. But always remember that here first factor is steric hindrance according to priority. First you have to see always by steric hindrance, then by the electron density. More steric hindrance means less reactivity towards nucleophile, and more electron density on carbonyl means less reactivity towards nucleophile. So from these two factors, again you can get questions in your examination, right? Now let's see few questions from this nucleophilic addition, and by that also you can understand the examples of nucleophilic addition reaction. And if you want, again, you can do it by your own. Pause the video. First, try by yourself. Later on, you can match your answers. So question is, complete the following reaction. Now, if you observe carefully, here the substrate is a ketone. We are reacting ketone with HCN. So of course, cyanide will attack on this carbon. The pi bond will break. Oxygen will attach with H+. You get OHCN, which is called cyanohydrine. And when this cyanohydrine is treated with concentrated H2SO4, means hydrolysis in the concentrated H2SO4 medium. So again, see, once in this session only, I have told you that when you do hydrolysis of cyanide in acidic medium, so that cyanide converts into carboxylic acid, right? And because you are heating it with concentrated H2SO4, so this alcohol, it will go through dehydration. So two things will happen, two processes will happen here. On one side, this OH group, right, this alcohol group will go through dehydration, and on the other side, this cyanide will hydrolyze into COH. So ultimately, the product C should look like this. Due to elimination, right? Suppose from here OH, from here H getting eliminated, you get a double bond here, and this cyanide will hydrolyze into carboxylic acid group. So this should be your product. Now check out the options. If you see carefully, it's not second, it's not first, no CHO, it should be fourth. The answer should be fourth. The answer should be fourth. And fourth is your answer. And this question, again, students, we got in the NEET 2023 examination, right? So let's not stop here. Let's do more questions from the nucleophilic addition reaction. Can you answer this? Which of the following reaction is not an example of nucleophilic addition reaction? Okay, which of the following reaction is not an example of nucleophilic addition and elimination? Means in which case both addition elimination is not happening. So let's check one by one, right? But this time from the reverse side. Can you see this D option? CS3CHO, CS3CHO, acetaldehyde, when it is treated with NH3, ammonia, you know very well that in first step you will have nucleophilic addition reaction. N will attack on carbon, pi will move on oxygen, one of the proton will be going to oxygen. So you will get addition product like this, CS3, C, H, OH and NH2. Now remember I told you one thing, that whenever ammonia or ammonia derivatives, they go through nucleophilic addition, so automatically they will have dehydration also. So here they will have auto dehydration. And after auto dehydration, this OH, this H will be removed. So you will get a double bond here, and this is your product. So in this case, in D, first we are having nucleophilic addition, but later on we are having elimination as well, right? And same thing you can notice in option C, because here you have a derivative of ammonia, it is a hydrazine. In B also, right? Hydroxyamine. So in BCD, automatically you will have a nucleophilic addition followed by elimination. But in the A option, if you notice, right, NaHSO3, sodium hydrogen sulfide, in this case, if you notice, the HSO3 minus, it is simply getting added onto the carbonyl carbon, right? Later on, you are having OH and SO3 Na groups, but here we are not having elimination. This is simple nucleophilic addition reaction. But in BCD, we are having nucleophilic addition and then elimination. But in option A, we are having only nucleophilic addition. Now they are asking in which case elimination is not happening. So answer will be A. Answer will be A, right? And this question again, we got in the NEET 2022 examination, right? Let's do few more. Let's do few more. Can you do it now by your own? It's a conversion question. The product formed from the following reaction sequence, right? And question is, first you have benzaldehyde. First you have benzaldehyde. Acha, okay, when this HCN will react, you know that nucleophilic addition will happen. So cyanide will attack on carbonyl, pi bond will move on to oxygen. So initially by addition of HCN, you will get carbon, CN, OH and H, cyanohydrine. Now this cyanohydrin is getting hydrolyzed. So this cyanide will convert into carboxylic acid. After hydrolysis, you get this benzene, CHOH, COOH. And later on, you are treating this with NaOH and calcium oxide. Do you remember NaOH calcium oxide? It is called soda lime, and soda lime has only one task. It removes CO2 group. It is used for decarboxylation. So when you do decarboxylation here, when you treat this with NaOH and calcium oxide, that means soda lime, what will happen? This CO2 part will be completely eliminated. This H will transfer here on this carbon, and your final product will be benzene, this carbon, hydrogen, hydrogen, and OH. So this is nothing but benzyl alcohol, benzene CH2OH. So here the product should be benzyl alcohol, and if you check out the options, right, the second option is the one in which you have the benzyl alcohol. So here answer should be second, and yes, your answer is second. Right? So now you can understand from nucleophilic addition what type of questions you get, and this we got again in NEET 2022 examination. Now, can you do this matching, all of you? It's a question of nucleophilic addition only, right? On the left hand side, we have the products formed after nucleophilic addition, and on the right hand side, we have the reagent. So, the first option, if you notice, it is cyanohydrin. We saw very well that we get cyanohydrin when aldehyde ketone, they reacts with HCN. So cyanohydrin here, it will be matched with HCN. I also told you that acetyl, hemiacetyl or ketyl, hemiketyl, these we get when aldehyde ketones respectively, they react with alcohol. So B here, it should match with alcohol, right? Now, if you talk about Skiff base, so Skiff base is very simple. It is again ammonia derivative. So Skiff base is nothing but RNH2. And oxime, it's very famous, right? Oxime is nothing but NH2OH. So the last two, that means Skiff base and oxime, they are also very important for you. And Skiff base you get from this RNH2, and oxime you get from NH2OH, hydroxylamine. So in this case, if you check out the options, so A should match with 4 and B with 3. So A4, B3 is only in one option, that is D. So answer should be D here. Yes, D. And I suggest one thing to all of you. Like if you check your NCERT, so in NCERT, after this nucleophilic addition reaction, a table is given, a box is given, right? And inside that box, you will notice that all the ammonia and ammonia derivatives, their reagents, and when they react with aldehyde ketone, so what product you get, it is written. So please go through that always before your examination. Please revise that box, right, before you give any examination. Correct? So in this case, your answer will be D, of course. And this question again, we got in NEET 2022. Now, can you do by your own this time, all of you? Can you do this question by your own? What is the IUPAC name of the organic compound formed in the following reaction? So reaction is, we have acetone. Acetone, you know very well, it is CS3. C double bond O, CS3. So acetone is treated with ethyl magnesium bromide. Ethyl magnesium bromide is CS3, CH2, MgBr. In the Grignard, you know very well that it is always minus, it is always plus. So if you treat with Grignard, it will go through nucleophilic addition. How? This C minus will attack on the carbon, pi bond will go to oxygen. Oxygen will take the Mg plus, but later on when you do protonation, so that oxygen will grab H plus from the medium, and ultimately the product will be CS3, C, CS3. On this carbon, now you have this CS3CH2 group, CH2CH3 group, and this oxygen after protonation, it will give you OH. So this is an alcohol, and if you write down the IUPAC name, so you know that OH is the prior functional group here. Numbering will be done from left hand side, 1, 2, 3, 4. Its name will be 2-methyl butane 2-ol. 2-methyl butane 2-ol. 2-methyl butane 2-ol. Answer should be B. So it's a very simple question of nucleophilic addition whose answer is B. And this question, students, we got in the NEET 2021 examination, right? Now, can you do this one? A similar type of question. The reaction between acetone this time the reaction between acetone, and now we have methyl magnesium chloride. Methyl magnesium chloride, C minus Mg plus. What product it will give? So again, this C minus will attack here, pi bond will go here. Initially O will attach with Mg, but when you do acidification, hydrolysis, so that OMg will convert into OH. So your ultimate product will be CS3, C, this CS3, CS3 and OH. This is nothing but a 2-methyl propane 2-ol, but if you check the common name, so this is tertiary butyl group. I hope you remember this. This is tertiary butyl. So you will be getting tertiary butyl alcohol here, and the answer will be B. And this question we got again in the NEET 2020 examination, students. Now, after nucleophilic addition, right, the next reaction of aldehyde ketone that you should know, and it is again very important for you, is partial reduction. Okay, like before we begin with partial reduction, let me tell you one thing with which you can remember the reactions of aldehyde ketone collectively is, students, for aldehyde ketone, we have total 4 types of reaction. Please remember like this, 4 types of reaction. One is a nucleophilic addition reaction that you saw. The second one is reduction. In reduction, we have partial reduction, strong reduction. Then the third one is oxidation. And then fourth one is Aldol reaction and Cannizzaro reaction. So like this, you can memorize all the reactions in your brain, right? So after nucleophilic addition, the second reaction is reduction. And in reduction, when you talk about partial reduction, so partial reduction means when your aldehyde ketone is converted into alcohol. Point is, you take aldehyde or you take ketone. You take aldehyde or you take ketone. If you treat aldehyde ketone, students, with lithium aluminium hydride, LiAlH4 or NaBH4, sodium borohydride. So with LiAlH4, NaBH4, it will reduce into alcohol. And logically in this reaction, what will happen? From your carbonyl, this pi bond of this carbonyl, it will break and hydrogens will be added. One hydrogen will be added on this carbon and one hydrogen will be added on this carbon, right? So after that, your product will look like RCH. One hydrogen will be added on this carbon, right? And again, you have this oxygen. So one hydrogen will be added here. Clear? And similarly, if you talk about ketone, so in ketone also, when you add LiAlH4, NaBH4, the pi bond of your carbonyl will break and hydrogens will be added. So in this case, your product will be RCR-O, and again, one of the hydrogen will be added here at oxygen and one at this carbon. So from aldehyde ketone, by partial reduction, you can obtain alcohol, but more precisely, if you do reduction of aldehyde, you get primary or 1-degree alcohol, and if you do reduction of ketone, then in that case, you get secondary or 2-degree alcohol, right? Now, one thing you need to understand and you need to be careful here. Whenever NaBH4, LiLH4 is used, so along with that, you have water, right? With LiLH4, NaBH4, along with that, you will have water. And I am saying that on carbonyl, hydrogens are getting added. One hydrogen is adding on this carbon, one hydrogen is adding on this oxygen. So point is, the hydrogen which is getting added to carbon, this hydrogen is coming from your LiAlH4. Remember like this, in this partial reduction, your LiAlH4 will give you H minus part and water will give you H plus part, right? And you know the polarity later on, carbon has delta plus charge, O has delta minus charge. So from LiLH4, the H minus which is coming, it will attach on carbon, and from water, the H plus is coming, it will attach on oxygen, right? Because sometimes they will play with isotopes. Like suppose if they give you LiAlD4, deuterium, and H2O. So in that case, carbon will have deuterium, oxygen will have hydrogen. If they give you LiAlH4 and D2O, so in that case, from LiAlH4, H minus will attack on carbon, and from D2O, deuterium will attach on oxygen. So you need to be careful here that from LiAlH4, you are getting H minus, and from H2O, you are getting the H plus. And by partial reduction of aldehyde ketone, you are finally getting 1 degree and 2 degree alcohol. One more point is there. I hope you know it from the alcohol chapter itself, that NaBH4 and LiAlH4, they do not affect CC double bond. NaBH4, LiLH4, they will not affect carbon-carbon pi bond. They affects only carbon-nitrogen pi bond, carbon-oxygen pi bond, hetero pi bonds, right? And one more thing, LiLH4 is stronger than NaBH4. NaBH4 is mild. And if you talk about NaBH4, so NaBH4 can reduce aldehyde, ketone, and acid chloride. NaBH4 will not reduce rest of the carbonyl compounds, like NaBH4 will not reduce carboxylic acid or ester or anhydride. NaBH4 can reduce only aldehyde, ketone and acid chloride. But LiLH4, it can reduce all carbonyls, like LiLH4 can reduce aldehyde, ketone, acid chloride, right, ester, anhydride, all. Correct? So these points regarding NaBH4, LiLH4 you should remember. Now, let's do some questions from this partial reduction, right? So that you have a better understanding regarding the reagent NaBH4 and LiAlH4. Can you do this? The major product formed in the following reaction. Now, if you notice, in this case, in your substrate, you have two functional groups, right? One is ketone, right? And one is, okay, again, another ketone. One is cyclic, one is open chain. And when you treat ketone with NaBH4, you know what will happen. NaBH4 can reduce ketone into alcohol. So initially, it will give you, the reduction of this ketone will give you OH, and then CH2, then C, again OH, H, CS3. So by treatment with NaBH4, initially you get this product. But here, further we are treating with H2SO4 and heat. You know that alcohol with H2SO4 heat, it goes through dehydration reaction. And in dehydration reaction, you get product by Setzeff rule. You get product by Setzeff rule. So if you do dehydration here, so according to Setzeff rule, from here, if OH and hydrogen gets removed, so from here you get more stable alkene or more substituted alkene, right? And CH, from here, if a hydrogen is removed with OH, and if you get here double bond, then this double bond will be resonance stabilized. So this will be the major product according to Setzeff rule. So this should be your product. Two double bonds, and they should be resonance with each other. Only option is there in which we have two double bond and they are in resonance is first option, right? Can you see this? Pi, sigma, pi in conjugation, right? And Setzeff rule says that during elimination we get more stable alkene as major. So according to Setzeff, we got our product as first. So first should be the answer, and yes, it is. And this question, students, we got in the NEET 2023 examination. Now, can we do one more again from the reduction or partial reduction of aldehyde ketone? Quickly. You can do it by your own again. Pause the video. Do it first by your own. Later on, you can confirm your answer. So identify the final product D obtained in the following sequence of reaction. What's the sequence? You have acetaldehyde treated with LiAlH4 and H2O. So it will convert into alcohol. A will be CS3, CH2, OH. Then it is treated by H2SO4 heat. So it will cause dehydration. So B will be ethene, CH2, double bond CH2. You know, elimination, right? From here, hydrogen will go out, from here, OH. Then you treat with HBr. So HBr will do simple electrophilic addition reaction. So C will be like CS3, CH2, Br. And now if you treat bromoethane with bromobenzene with sodium diether, I think this is a reaction from your haloarenes chapter, right? It is nothing but Woods-Fittig reaction. Remember, sodium will give electron to remove this bromine and this bromine, right? And here you get a radical, here you get a radical. So these two radicals will combine to give you ethyl benzene. The benzene and this CH2 CH3 group will combine. So your final product should be ethyl benzene. Where is ethyl benzene? In which option? It's not second, fourth, it's the first one. So again, in this case, the answer will be first. But again, of course, answer is 1. But in this question, we had so many concepts, right? We had partial reduction of aldehyde, we had dehydration of alcohol, we had electrophilic addition of alkene, and then we had Wurtz-Fittig reaction. So conversion questions will be like this only, right? They will ask by combining multiple reactions together, right? And this they asked in the NEET 2023 exam. Now, can you answer this again from the partial reduction concept, all of you? Question is very simple. What is the major product formed in the following reaction? Now here, if you look at your substrate, so one group you have as ketone, and this is C double bond O CH3, this is ester. Now a compound having ketone ester, if you treat with NaBH4, so you know that NaBH4 has its own limitations, right? NaBH4 can reduce ketone, but it cannot reduce ester group, right? NaBH4 can reduce ketone, aldehyde, acid chloride, but it cannot reduce ester. So when you treat with NaBH4, this will be reduced into alcohol, but ester will remain as it is. So if you check out the options, here both reduced, not possible. Here OH, yeah, second is your answer, right? The ketone will be reduced into alcohol, but ester part should be as it is. Ester part should be as it is. So here second should be your answer. And yes, answer is 2. And again, this question, students, we got in the NEET 2021 examination, right? Let's move ahead. And now let's discuss the next reaction, which is kind of, you can say that previously we saw partial reduction, and now we are going to look into the strong reduction, right? When you do strong reduction of carbonyl, so the carbonyl group converts directly into CH2, right? If you have a simple aldehyde ketone, so by strong reduction, it will convert into alkanes, right? And in the strong reduction part, the first one is Clemenson reduction. In Clemenson reduction, in Clemenson reduction, the first thing that you should remember is the reagent, right? In Clemenson reduction, we use zinc amalgam, right? Along with HCl. So it is a reaction of acidic medium, and it is a metal acid reduction, right? You know what is metal acid reduction, right? In which your metal will give you the electrons, and the HCl, the acid, will give you the H plus ion. Now, what it does, like if you take a carbonyl compound like aldehyde or ketone, right, and you treat that with zinc amalgam HCl, right, so it will directly convert the carbonyl group into CH2. This C double bond O part, it will be converted into CH2 part. So the product will be RC H2 and H. So basically, in your substrate, if you don't have any other functional group other than carbonyl, so then your product will be simply an alkane. Like for example, if I take CS3, C double bond O, H, right? If I take acetaldehyde and I do the same, I put zinc amalgam and HCl. So this C double bond O part, it will convert into CH2. So in this case, your product will be CS3, which is nothing but ethane. So you can also say that Clemenson reduction is a way to prepare alkane from your aldehyde ketone, right? And please always remember that Clemenson reduction is used in acidic medium. It's a reaction of acidic medium. Now, just like Clemenson reduction, we have one more, which is nothing but a Wolff-Kishner reduction, right? And in Wolff-Kishner reduction, your reagent is hydrazine, NH2, along with base, that is KOH. But point is, Wolff-Kishner is a reaction of basic medium, right? Here the medium is basic, but overall, it also does the same work, right? It also converts carbonyl, if you take aldehyde ketone and you treat with hydrazine and base, so it will also convert this carbonyl into CH2, right? The major difference is, if you talk about Clemenson and Wolff-Kishner, the major difference is Clemenson is of acidic medium, Wolff-Kishner is of basic medium. Also, Wolff-Kishner is very much selective, right? Like in your substrate, suppose other than carbonyl, if you have some other functional group, and then if you do reduction. So by Wolff-Kishner, only the carbonyl group will be reduced. But if you do Clemenson reduction, then there is a possibility that other groups, other than the carbonyl, whatever groups are present, so they are also altered by the Clemenson reduction. So that's why whenever we have to do selective reduction, we perform Wolff-Kishner reduction. Wolff-Kishner reduction, right? Now, after reduction, after Clemmensen and Wolff-Kishner reduction, if you talk about the oxidation reaction of aldehyde ketone students, so oxidation reaction is very simple for aldehyde ketone. Why? Because whenever you try to oxidize any aldehyde, so ultimately it will get converted into carboxylic acid, right? You use any strong oxidizing agent like KMnO4, K2Cr2O7, Jones reagent, or whatever oxidizing agent is there which can oxidize the aldehyde group. So aldehyde group is always oxidized into carboxylic acid. Only one thing you need to take care of is that if your oxidation is happening in basic medium, right? So in basic medium, instead of acid, you get carboxylate ion, right? So in acidic medium, if you are doing oxidation, then you get simple carboxylic acid. If you are doing oxidation of aldehyde in basic medium, then you get carboxylate, right? So oxidation of aldehyde is so simple. You always get acid. And on the other side, if you talk about ketone, so ketones are very hard to oxidize, right? It is very difficult to oxidize ketone under normal condition. We need vigorous condition, extreme conditions to oxidize ketone, or we need extremely strong oxidizing agents to oxidize ketone. But if you talk about ketone, so by the oxidation of ketone also, students, you will be getting acid only, right? Suppose if I take unsymmetrical ketone like this, CS3, CH2, CO, right? CH2, CH2, and CS3. So intentionally I have taken unsymmetrical ketone, because when you oxidize ketone, right, with vigorous condition, right, like HNO3 or very high temperature pressure. So under vigorous condition, when you oxidize ketone, so ketone is oxidized according to Popoff's rule. Please remember that. Popoff's rule. What Popoff's rule says, that when you do oxidation of ketone, especially the unsymmetrical ketone, then the smaller alkyl group will remain with the carbonyl. So in this case, around your carbonyl, this is your ethyl group, this is your propyl group. So definitely ethyl is small. So carbonyl will stay with the ethyl group. And during oxidation, of course, here CC bond will break. So this CC bond will dissociate, and this carbon will oxidize into acid, and this carbon will oxidize into acid. So in this case, you will be getting CS3, CH2, C double bond OOH from this. And from this side also, you will be getting CH3CH2, and this CH2 will oxidize into COH. So you will be getting 2 molecules of propanoic acid. So first thing is, aldehydes oxidize to acid. Ketones are difficult to get oxidized, and by chance, under extreme condition, if you oxidize ketone, so in unsymmetrical ketone, it is oxidized according to Popoff's rule, which says that carbonyl group will remain with your small alkyl group, right? Now, point is, because oxidation reaction is easy in this chapter, so that's why we have added certain name reactions under the oxidation part. And those name reactions are important for you. Those tests are important for you. Like one of the oxidation reaction is Tollens reagent. And Tollens reagent used, right, when it is used, so to detect or to distinguish anything, then it is called as Tollens test. So the same reaction you can also consider as Tollens test. Tollens test. So first let's understand what is Tollens reagent. Students, Tollens reagent is ammonical silver nitrate. It is ammonical silver nitrate. So try to understand like this. It is a mixture of NH3 and AgNO3. But when you mix NH3 with AgNO3, it will create a complex like this. Ag NH3 whole twice plus. So either your Tollens reagent can be represented like this, AgNH3 whole twice plus, or it can be represented like a mixture of NH3 plus AgNO3. Both are same, both are Tollens reagent. Point is, Tollens reagent is oxidizing agent here in this aldehyde ketone chapter. So of course, it will not oxidize your ketone group. That's why it is used to distinguish aldehyde ketone. because aldehydes, right? Aldehydes, they will give tolerance test, but ketone, a simple ketone, will not give tolerance test. But as I told you that tolerance reagent will act as a oxidizing agent here. So the reaction part will be very easy, right? If you take any aldehyde and if you react that by tolerance reagent, so ultimately it will get oxidized, right? It will get oxidized into carboxylate ion because the reaction is happening in basic medium. So I can't write COH, I will have to write CO minus. And the Ag ion will be reduced into pure silver. That's the reaction here. With tolerance reagent, aldehyde converts to carboxylate ion and Ag plus is reduced into Ag, correct? And this reaction is not shown by simple ketone, but there is a case in which ketone can also show, ketone can also react with tolerance reagent. And that case is alpha hydroxy ketone. But in that also not all alpha hydroxy ketone, those alpha hydroxy ketones in which due to tautomerism, your ketone can convert into aldehyde group. So one of the example of this is fructose. If you remember your biomolecule chapter, so in your biomolecule you have fructose. Fructose has this kind of structure, CH2OH, C double bond O, and so on. And this is your ketone group, this is your alpha carbon, and your alpha carbon has OH, right? So alpha hydroxy ketone, which can tautomerize into aldehyde, in which due to tautomerism the ketone will convert into aldehyde group, and then it will give tolerance test, or then it will react with your tolerance reagent. So alpha hydroxy ketone sometime and all the aldehyde, they react with tolerance reagent. But any of the simple ketone like acetone, right, acetophenone, benzophenone, they will not react with your tolerance reagent. I hope that you will remember tolerance reagent within this chapter like this for aldehyde and ketone. Now, after tolerance test or tolerance reagent, right, let's see one question from the same. Can you do it by your own? Identify the major product obtained in the following reaction. Now, if you notice, in the substrate we have a aldehyde group here and we have a ketone group here, a simple ketone, simple aldehyde, and we are treating it with ammonical silver nitrate, which is tolerance reagent. This is which is tolerance reagent. So if you treat it, the aldehyde part, it will oxidize into COO minus, but ketone part will remain as it is. So in your major product, you can say that aldehyde will convert into COO minus, but ketone will remain intact, right? And the only option in which this is happening is option 3, right? In option 3, you can notice that CHO is converting into CO minus and ketone is as it is. So in this case, the answer will be 3. And this question, students, you got in NEET 2023. So it's a very recent question, right? And tolerance test is very, very important, not only for this chapter, right? In hydrocarbons also you talk about tolerance reagent, right? If you remember, tolerance reagent also reacts with terminal alkyne, but it will not react with non-terminal alkynes, right? So in hydrocarbons chapter also you talk about that tolerance test or tolerance reagent, right? Now, just like tolerance reagent, we have another failing reagent here or failing solution here, and it is again a mixture. Like if you notice, tolerance reagent is a mixture of ammonical silver nitrate with ammonia. So similarly, failing solution is a mixture of CuSO4, copper sulfate, along with sodium potassium tartarate, or commonly called as Russell salt. This is your sodium potassium tartarate, OHOH, HH, COOK, and COONA, sodium potassium tartarate, or commonly called as Russell salt. So mixture of this Russell salt and copper sulfate, this is called as failing solution, right? Even your failing solution reacts in basic medium, but again point is same. Failing solution also acts as oxidizing agent with aldehyde. So again in the reaction same thing will happen. Just like your tolerance reagent, even if you put your failing solution with aldehyde, so in the reaction part same thing will happen. You take aldehyde, you treat with a failing solution, the product will be carboxylate ion. But the point is, failing solution is weaker than tolerance reagent. So tolerance reagent, it can oxidize any type of aldehyde, whether it is aliphatic or aromatic. But please remember that failing solution, it will not oxidize any of the ketone first. Also, it will not oxidize your aromatic aldehydes. Right? That's why most of the time failing solution is used to distinguish aromatic aldehyde with aliphatic aldehyde. So failing solution is mainly for your aliphatic aldehyde. It can convert aliphatic aldehyde into carboxylic acid or carboxylate ion in the basic medium. But for these reactions, the most important point is you should remember the formula of the reagent. Tolerance reagent, failing solution, correct? Similarly, we have another reaction in the oxidation part only, which is called iodoform reaction. And it is also used as a test, right? Of especially ketone and alcohol. Iodoform reaction you will see in 2 chapters. It is there in this chapter, aldehyde ketone, and iodoform reaction is also there in your alcohol chapter. Why? Because we will see the reaction, but when you talk about iodoform reaction as a test, so it is used to identify those compounds in which we have either this structure, means a carbonyl attached with CH3, or this structure, an alcohol having 1 hydrogen at least on the alpha carbon, right? And of course, it should have a CH3 as well. So an alcohol having methyl group on the alpha carbon and a ketone which is attached with methyl group on one side, in any compound you have, if you find these 2 structures in them, so they can give you what? They can give you iodoform test. And in the iodoform reaction, during the iodoform test, what happens? You take, in this chapter, why we are talking about iodoform reaction? Because it can used to oxidize methyl ketone. Anyway, we have seen that ketones are difficult to oxidize, but at least the methyl ketones, it can be oxidized by iodoform reaction. So if you take a methyl ketone and you treat with iodine NaOH, so this is the reagent of your iodoform reaction, correct? So if you treat it with I2 with NaOH, and sometimes you will notice that instead of writing I2 NaOH, they can write it like this, NaIO or NaIO3. So please do not get confused. Even if they write NaIO or NaIO3, so they are same as I2 NaOH, because in your P block you will study that I2 NaOH, when they react, it produces NaI along with NaIO and NaIO3. And this NaI and NaIO3 can function as oxidizing agent. So either they can write I2 NaOH, or instead of I2 NaOH, they can write these 2. Now the reaction is, when you treat methyl ketone with I2 NaOH, it gives you RC double bond O minus. Again, I can't write OH because it's a basic medium reaction. And along with that, you get CHI3. CHI3 is your byproduct. This is called iodoform. And this is one of the reactions in which the name of reaction has been kept on the basis of byproduct. The byproduct is iodoform, and that's why the reaction is called as iodoform reaction. And overall, if you see what is happening in this reaction, so this CC bond is having fission. This part is getting oxidized into acid RCOO minus, and this CH3 is converting into CHI3, right? And if I talk about a little bit of mechanism, right, then this reaction happens, or the cause of this reaction is acidic nature of alpha carbon. I hope you remember very well that when we have a carbonyl, the alpha carbon of carbonyl, they are acidic in nature. So point is very simple. The alpha carbon is acidic in nature, right? And if you treat with NaOH, which is a base, so NaOH can take this H plus, right? Then this electron pair can go to carbon, and then that electron pair can be given to iodine. So iodine will act as oxidizing agent here. And one by one, 3 times this will happen. 3 times this CH bond will break, H plus will be taken by NaOH, and 3 iodines will be attached with your carbon. So by 3 time iodination, finally, you get this product, Ci3, right? And at the end, right, this CC bond will break with help of NaOH, right? From NaOH, the hydrogen will attach with carbon and ONA part will attach with carbonyl, right? You get CHI3 and sodium carboxylate. But point is, in iodoform reaction, you need to focus only on 2 points. What is your reagent? I2NaOH. And then which compounds can give iodoform reaction? Alcohol and ketone. Ketone attached with methyl group, alcohol having methyl group on the alpha carbon. So these 3 reactions or tests are important for you in the oxidation. Iodoform, failing solution and tolerance test or tolerance reagent, right? Now, finally, after the nucleophilic addition, reduction and oxidation, right? We have a reaction for aldehyde ketone, which is again very much important for you and known as aldol condensation. I hope you know this aldol condensation very well. It is a reaction which happens due to alpha hydrogen in your aldehyde ketone, right? And the reagent of this reaction is dilute NaOH. Okay, most of the time we use base for aldol condensation, but that's not a mandatory thing. Aldol condensation can happen in acidic medium also, right? So we can have base catalyzed aldol condensation, we can have acid catalyzed aldol condensation or aldol reaction also. But we talk about mostly, right, base catalyzed aldol condensation or aldol reaction. Now, see, according to me, if you want to remember aldol condensation, just remember the first step. The first step of aldol condensation is the base will come, it will grab one of the H plus from the alpha carbon and then it will create a carboanion, and that carboanion will go through nucleophilic addition. I hope you all know very well about nucleophilic addition because we already saw that. So in aldol condensation, first step is formation of carboanion, but after that the second step is simply nucleophilic addition. So let me take an example here, the most famous example. Let's say I take CS3CHO, right, and I put dilute NaOH in it. And please remember, if I put only dilute NaOH, it is aldol reaction. But if I put heat, then it is called aldol condensation. Right? I will tell you what's the difference between these two very soon. So what happens here, in your substrate, right, you can notice that for your carbonyl, this is your alpha carbon. And on your alpha carbon, definitely you have a hydrogen, you have a CH bond, because this is the prime condition of aldol. For any aldehyde ketone, aldol reaction will only happen when your alpha carbon has hydrogen. So this alpha carbon has hydrogen. So in the very first step, the NaOH, the base, it will come, it will take away the H plus and this CH bond, electrons of CH bond will remain on the carbon. So you get your intermediate, which is carboanion, like this, right? C double bond OH. Now this carboanion, it will require some positive center. In this reaction, we are adding only the carbonyl compound. So what it will do, it will take another molecule of the aldehyde here, because in the aldehyde, in the carbonyl, the carbon is a positive center, right? So this carbanion, in the second step now, it will attack on the carbon of carbonyl, and from here it is nucleophilic addition. Carbanion is a nucleophile, so it is going to add on this carbon, the pi bond will go on to oxygen, and this oxygen will take a H plus from the medium, right? And ultimately, after addition, you will get this product. Here, whenever you are writing the product, please be careful, right? So first we have a CHO group. I am writing here, CHO group, this one. Then we have CH2, then we have CH2. Then this CH2 is getting attached to this carbon, which has a hydrogen and a CS3. And the carbonyl of this carbon will now convert into OH. So this is called your aldol product, students. Because here you have a aldehyde group and alcohol group. So this is called aldol product. But, if I put only dilute NaOH, my reaction will end here. But if I put heat, so heat can cause dehydration. So in the presence of heat, if I heat this further, what will happen is still this alpha carbon is acidic. So we have acidic hydrogen here, we have OH here. So this OH and hydrogen will be eliminated, and then you will get, or then you are left with aldehyde group, CH, double bond, CH, CH3. So after condensation, now you have a alkene and aldehyde group. But before condensation, only by aldol reaction you get aldol product. So isn't it very simple? The aldol reaction or aldol condensation. Base will take the H plus, it will create a carboanion. The carboanion will attack on another carbonyl group, right? And here, both molecules are same, so it is called aldol reaction. If you take two different types of aldehyde ketone, then it is called cross aldol reaction, right? If you have two carbonyl group present in the same compound, then it is intramolecular aldol condensation. So we can have different types of aldol condensation, but every time the concept will be same. Base will take H plus, it will create a carbanion, and then carbanion will attack on the carbonyl group, right? So I hope you have understood the mechanism, the concept of aldol condensation. So let's see few questions now from this aldol condensation reaction. Can you do it with me, all of you? If you do it before me, I will be very, very happy for you. Consider the given reaction. We have CH3COCH3, it is acetone. It is treated with base, dilute barium hydroxide, dilute NaOH, barium hydroxide, all are bases, right? X. Okay, they are not heating here, right? But barium hydroxide is a strong base. The functional groups present in the compound X are. But first thing is, I hope you have understood, if I take a aldehyde ketone, which has alpha carbon and alpha hydrogen. So alpha hydrogen containing aldehyde ketone or aldehyde in the presence of dilute base, it will give you aldol reaction. So first of all, I think you have understood that it is a aldol reaction, correct? And definitely in this case, your answer will be D, that means alcohol and ketone. Why? Because we are not heating it, right? We are not heating it. So it is a simple aldol reaction. When you heat that, so then it is aldol condensation. If you want, I can write the reaction for you, but I hope you can do it, right? This much you can do now, right? Like in the very first step, the base will grab the H plus. So you get this type of carbanion, CH3, C double bond O, CH2 minus. Now it will look for a carbonyl. So another molecule of the acetone you will take CH3, C double bond O, CH3. Now this carbanion will attack on this carbon, pi bond will shift here. So you will be getting CH3, C double bond O, CH2. Now this CH2 attached with this carbon, which has two methyl group, and this carbonyl will convert into OH, right? So this is your aldol product. Aldol product has ketone here and alcohol here. So ketone and alcohol was our answer. But point is, if I heat this, which is not given in the question, if I heat this, then I will have dehydration, right? And then after dehydration, if you do dehydration, then your answer should be A. Then your answer should be A. So for aldol, the answer is alcohol ketone, and for aldol condensation, the answer is ketone and double bond. But ketone and double bond you get only when you heat. So without heat, it will be simply alcohol and ketone. And students, this question we got very recently in the NEET 2023 examination, right? Let's not stop here. Take your pen paper. Please do some workout here. Can you solve it? Which one of the following is not formed when acetone reacts with 2-pentanone? Now here, acetone is one compound, 2-pentanone is another compound. So we are taking two different carbonyls, right? In the presence of dilute NaOH means it is aldol condensation only, right? Followed by heating, right? Condensation. But because we are using two different aldehyde or ketone, so it is not a simple aldol, it is a cross aldol reaction. It is a cross aldol condensation reaction. Now point is, if you take acetone, so from acetone, you can get this anion as intermediate, right? And if you talk about 2-pentanone, so from 2-pentanone is C, 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 and on second carbon you have this. So here also you have acidic hydrogen, here also you have acidic hydrogen. So from 2-pentanone you can get two type of carbonyl. I hope you are getting how we are getting the carbonyl in the first step. The base will take the alpha hydrogen. So from acetone, if the base takes alpha hydrogen, you get this anion. And from 2-pentanone, if your base takes alpha hydrogen, you can get anion here also and here also. So two possibilities. One is this CH2 minus C double bond O, then CH2, CH2, CS3, and another anion you can get from 2-pentanone is CS3, C double bond O, CH minus, then CH2, CS3. So here three intermediates are possible, three anions are possible, right? And now these three anions, one by one, they can attack on both acetone and 2-pentanone, right? So by attacking them one by one, you can decide what are the total possible products. In this case, you will be getting total 6 products. Like the first anion, when it will attack on acetone, carbonyl of acetone, for nucleophilic addition, you will get one product. This anion, when it will attack on carbonyl of 2-pentanone, you get another product. Similarly, the second anion, it can attack on acetone for nucleophilic addition and 2-pentanone, right? So similarly, the third, it can attack on acetone and 2-pentanone. So total of 6 products you will be getting, and one by one if you check, you can get your answer, and your answer will be of course 3 here. Your answer will be 3 here because they are asking which one. The third you can't get. So first, second, third, first, second and fourth you will get as your product, one of the product, but third you will never get as your product. I hope that you will do the further nucleophilic addition here, right? I told you have 3 anions, and one by one these 3 anions can attack on both acetone and 2-pentanone, right? And your answer is third, and this question we got in NEET 2022 exam. Now, can you do one more? Reaction between benzaldehyde, benzaldehyde is this, benzene CHO. Reaction between benzaldehyde and acetophenone, acetophenone is this. With dilute NaOH is known as, if you notice, in benzaldehyde you don't have alpha hydrogen, but in acetophenone here you have alpha hydrogen. So out of 2 carbonyl, if any of the carbonyl has alpha hydrogen, it will be aldol reaction. It will be aldol condensation reaction, cross aldol condensation reaction. So definitely it's not Cannizzaro. Cannizzaro we will see very soon. It's not cross Cannizzaro. It is cross aldol reaction. It is cross aldol reaction, cross aldol condensation, and your answer is C. And this simple question where they are just asking the name of the reaction, we got in NEET 2020 exam, right? Let's do one more from the aldol condensation reaction. Can you do this? Of the following, which is the product formed when cyclohexanone undergoes aldol condensation? So it is self, right? It is self aldol condensation. Only cyclohexanone is there, so it will be easier for you. Cyclohexanone is this. So you have 2 alpha carbon, but both are symmetrical. So suppose that from this alpha carbon, a proton is taken by the base. So here you get a carbonyl, and one compound has only one carbonyl. So another compound I will have to take for nucleophilic addition, right? So in the second step, this anion will attack here, pi bond will go here, and the aldol product you get initially, it will be like ketone, this carbon attached to this carbon, right? And here also you have a 6-membered ring, but on the same carbon where this is attaching, you have a OH group, right? This is aldol product. But here we are doing what? Followed by heating, means we are doing condensation. So when you do condensation, from the alpha carbon, one more hydrogen will be eliminated and you get a double bond here. So look at this structure now in the options, in which case you have a double bond between 6-membered ring and one ketone group. Only in the first option, right? Can you see this? Double bond between the 6-membered ring, and adjacent to that we have a ketone group. So answer should be first, and A is your answer. And this question, students, we got in the NEET 2017 examination. So now I think in aldol, because aldol is important, in aldol reaction or aldol condensation, you can do any type of reaction, whether it is self-aldol, whether it is cross-aldol, whether it is intramolecular aldol, because every time the mechanism will be same. So now after aldol, let's talk about the last reaction of your aldehyde ketone. It is Cannizzaro. And I always prefer to revise Cannizzaro with aldol. Why? Because in both aldol Cannizzaro, the reagent is base. The only difference is in case of Cannizzaro reaction, the base is concentrated because it has to participate in the reaction. And the other point is, when your carbonyl has alpha hydrogen, so then it will have aldol condensation reaction. But when your alpha carbon has no hydrogen, when you don't have alpha hydrogen in your carbonyl, in that case only you can have Cannizzaro reaction. So Cannizzaro is possible in case of formaldehyde, in case of benzaldehyde and all, right? And this reaction, when you treat, let's say formaldehyde with concentrated NaOH, in this reaction what happens? You have a simple hydride transfer, which is also your rate determining step, the slow step. In this reaction, what happens? You have your carbonyls. Of course, you don't have alpha hydrogen in it. So what happens? The base itself attacks on the carbonyl, right? When the base attacks on the carbonyl, very slowly, one of the hydrogen from this carbon will be transferred as hydride into the other carbonyl group. So here you have a hydride transfer, right? This hydride, when this NaOH will attack, this hydride will be eliminated from this carbon and it will be transferred to the other carbonyl group. So this H minus kind of, it is getting added on the other carbonyl. So on the other carbonyl, again you are having nucleophilic addition, right? And again this pi bond will delocalize onto oxygen. So this part where your NaOH is attacking, it will convert into Hc double bond O, ONA, Hc double bond ONA. And another molecule we need, so here also we need two molecules at a time, two carbonyls at a time. So another molecule, it will convert into CH3OH. Now if you notice carefully, here your aldehyde is converting into acid as well as alcohol. So it is also called as self-oxidation reduction, because during Cannizzaro, one of the aldehyde is getting oxidized into acid and one of the aldehyde is getting reduced into alcohol. So self-oxidation and self-reduction, right? Self-oxidation and self-reduction, correct? Similar type of reaction when you talk in redox. So in redox, similar type of reactions are called as disproportionation reactions also, correct? And in Cannizzaro also you can have cross Cannizzaro, right? Like suppose if you have a reaction between formaldehyde and benzaldehyde, so that is called as cross Cannizzaro. In cross Cannizzaro, always remember that carbonyl with less bulky group, carbonyl with less bulky groups will convert into acid, during the Cannizzaro reaction, and carbonyl with more bulky group will convert into alcohol according to the mechanism. The main thing here is NaOH will attack on the carbonyl, right, and it will transfer hydride from one carbonyl to another, right? And the one from which hydride is going out, it will be converted to acid, and the one at which your hydride is getting added, that will be converting into your alcohol. So this is called Cannizzaro or cross Cannizzaro reaction, right? So now students, we have done the major reactions of aldehyde ketone: nucleophilic addition, reduction, oxidation, and Aldol Cannizzaro. Apart from those, for the aromatic part, we also have electrophilic substitution reaction. You know very well, electrophilic substitution is a reaction of benzene. So here the aldehyde or ketone group, it will just act like a directing groups, right? Like suppose if you take a benzene, and on your benzene, if you attach aldehyde group, so aldehyde is electron withdrawing in nature. Aldehyde shows minus R effect with your benzene. It is deactivating in nature. So first thing is CHO will decrease the reactivity of benzene towards electrophile. And second point is it is always meta-directing. So whenever benzaldehyde reacts with any electrophile, any electrophile, whether it is Br plus, whether it is NO2 plus, whether it is CH3 plus, any electrophile. So electrophile will be added on the meta position, right? And same for ketone. Ketone also shows minus R effect, and with ketone also it is meta directing. So if a benzene ring has a ketone group to it, and if any electrophile reacts with that benzene, so the electrophile will be directed at meta position. So overall you can remember like this, that both aldehyde and ketone, they are meta directing when they are attached with your benzene ring. So now students, after aldehyde ketone, let's start with the next part of the chapter. You know that after aldehyde ketone, we have to discuss about carboxylic acid in the same chapter, right? So in the carboxylic acid, I hope you know the basic structure. It is C double bond OOH. But here again, before we proceed with the preparation and reactions of carboxylic acid, some of the common names are very, very important, right? So you need to remember them, like when it is HCOOH, so it is very common. I hope you know that, formic acid. And when it is COOH, it is called oxalic acid. And here you will notice a pattern, right? Here you have a two carboxylic acid group connected together, so we are calling it oxalic acid. And after oxalic, when you talk about malonic, so between COH, you are having a CH2 now. After malonic, if you talk about succinic, so between COH, now you have two CH2, right? In glutaric, you have 3 CH2. In adipic, you have 4 CH2. So you can remember this with a trick like Ohm's ga, right? O means oxalic acid, M means malonic acid, S means succinic acid, G means glutaric acid, A means adipic acid. In oxalic acid, you have COH. In malonic acid, one CH2 will be in between COH. Then in succinic acid, you have 2 CH2. And similarly for glutaric, 3 CH2. And adipic, you have 4 CH2. And also, when two carboxylic group, right, they are attached at ortho position in the benzene ring, so then it is called what? Phthalic acid. So these are some of the common names which you should remember always. And some of the common names I have not written it here because I assume that you know those names already, right? You know what is salicylic acid, you know what is acetic acid, right? So those parts you know very well. So after this common name, let's begin with the preparation of carboxylic acid. And here you will notice that most of the reaction will be already known to you, either from the aldehyde ketone part or from the alcohol phenol ether chapter part, right? Like the first preparation of carboxylic acid is from alcohol or aldehyde. So you can guess what will happen here. You take alcohol, and in alcohol you need to take only 1 degree or primary alcohol, because you cannot get carboxylic acid by the 2 degree or tertiary alcohol. So you take primary alcohol and you oxidize with strong oxidizing agents like KMNO4, K2Cr2O7. You will get what? You will get carboxylic acid, right? And if you take aldehyde, so just now in the aldehyde part we have seen that whenever aldehyde is oxidized, so we get what? Carboxylic acid. So whether it is aldehyde, whether it is primary alcohol, oxidation of both, strong oxidation of both can give you carboxylic acid. But please remember always that in the alcohol, you can't take secondary or tertiary alcohol to prepare carboxylic acid, right? After alcohol and aldehyde, the next method of preparation. Okay, before we go into next method, we have a question here for you also. Can you do this quickly? For the given reaction, KMNO4 H plus, what is P? What is P? If you notice carefully, it's a simple oxidation reaction, simple oxidation, right? KMNO4 is a strong oxidizing agent. So when you do oxidation of this, right, so this double bond will break, right? And this carbon, it will oxidize into aldehyde first because it has hydrogen. So first it will oxidize into aldehyde, but aldehydes are also oxidized by KMNO4. So ultimately that aldehyde will convert into acid. And even from this side, you get aldehyde first. You get aldehyde from both sides first, and then both sides later on, because KMNO4 is a strong oxidizing agent, the aldehyde will convert into acid. So here the final product should be 2 molecules of this, right? So your answer will be fourth here, and of course fourth is your answer. And I think if you remember, this reaction you have in your hydrocarbons chapter under the properties of alkene. If you see the oxidation of alkene, so this comes under strong oxidation of alkene. Strong oxidation of alkene can give you either acid or ketone, right? Depending upon what degree of carbon you have. And this question is very recent. We got it in NEET 2024 examination, correct? So after oxidation, right, of alkene, now we have another question again from the oxidation only. And here you can notice that whatever listed A, B, C, D, E, right, most of them are oxidizing agents. So reagents which can be used to convert alcohol, more precisely primary alcohol, into carboxylic acid. So basically whatever is there which is strong, like CrO3 with H2SO4 Jones reagent, it is strong. So A will convert primary alcohol into acid. K2Cr2O7 is strong. KMnO4 is strong. Copper and 573 Kelvin, it will do dehydrogenation, right? Remember, it will convert primary alcohol into aldehyde. So D can't be used to prepare carboxylic acid. And CrO3 with anhydride, right? This we use in the preparation of benzaldehyde, if you remember, right? So with CrO3 and this anhydride, you can't prepare acid, you can prepare benzaldehyde, right? So only A, B, C are the oxidizing agents which can convert 1 degree alcohol into carboxylic acid. So answer will be, of course, A, B, C means option C. And this question we got in the NEET 2023 examination. Now, after oxidation of aldehyde and alcohol, 1 degree alcohol, another way of preparing carboxylic acid is by oxidation only. And this is called side chain oxidation. In side chain oxidation, students, what's the point? You take a benzene attached with some alkyl group, like whether it is methyl, whether it is ethyl, doesn't matter. Whether it is methyl or ethyl, doesn't matter. If you do oxidation, right, always the carbon which is attached with benzene ring, that carbon will be oxidized. So in this case, this carbon is attached with benzene, so this carbon will oxidize strongly in the presence of strong oxidizing agents like KMnO4, and it will give you what? Benzoic acid, right? And even if you take ethyl benzene, so although you have two carbons in the side chain, but still the carbon which is attached with benzene ring, this will be oxidized, and here also you will be getting benzoic acid only. So it doesn't matter with your benzene in the side chain whether you have methyl, ethyl, propyl, right? Every time by strong oxidation with KMnO4, you will obtain what? Benzoic acid, right? Now, after side chain oxidation, I think this point I have told you already. Remember the preparation of aldehyde from Stephen's reaction. So there I said a point that when you take nitrile, and you do hydrolysis of nitrile in acidic medium. So in acidic medium, it will give you directly carboxylic acid. But please be careful. For the nitriles, if you do hydrolysis in basic medium, then it can give you amide. Then it can give you what? Amide. But in acidic medium, it will give you what? Carboxylic acid. So it's a very direct reaction. You take nitrile, you do hydrolysis in acidic medium, the cyanide group will directly convert into COH. And in some of the questions we have already seen, right, in the aldehyde ketone part, that direct hydrolysis of cyanide can give you what? Carboxylic acid. So here we have this as a preparation method of carboxylic acid, right? Now, after nitrile, a very famous method, Grignard reagent comes everywhere, right? From Grignard reagent, you can prepare aldehyde ketone. And now from Grignard reagent, you can also prepare what? You can prepare carboxylic acid. How? You take a Grignard reagent. Let me take an example. Let's say I have CS3 MgBr. You know very well that in CS3 MgBr, Mg is plus, CS3 is minus. That's the ionization always. Now, if you treat a Grignard with carbon dioxide, students, in carbon dioxide, if you check the polarity, so the carbon atom has some delta positive charge and oxygen has some delta negative charge. So out of your Grignard, the anionic part, it will attack on this carbon. One of the pi bond will ionize, it will go to oxygen, and later on the oxygen will grab the Mg plus part. So first with CO2 and Grignard, you will be getting an addition product which will look like this, right? C double bond O O minus, MgBr plus, and with this carbon, now you have that alkyl group CH3. And later on, if you do protonation, the Mg plus will be removed, right? H plus will come, and then your product will be C double bond O, CH3, and OH. So using Grignard CO2, we can easily obtain again carboxylic acid. So this is also a preparation method for us for the carboxylic acid, right? Now, can you answer this question, all of you, quickly? It should be very easy for you. Pause it, do it by your own. Later on, check the answer. So question is very simple. If I take Grignard with CO2 in dry ether medium initially, so I get Y, and hydrolysis acidification gives me acid. So what is this Y? So that Y is nothing but addition product, right? On the CO2, R will attach, one double bond will remain as it is, and one double bond will become single bond, and MgX plus will attach here, right? So in what option you have RCOO minus and Mg plus? In option B. So definitely here the answer will be option B, and this simple question we got in the NEET 2022 examination, right? So you will feel that preparation reactions of carboxylic acid is much simpler as compared to that of aldehyde and ketone, right? Now, the next method of preparation of carboxylic acid is from its derivative itself, right? Point is, whenever a compound is prepared with help of carboxylic acid, so that compound is called as acid derivative. But here we are doing it reverse. What we are doing, we are converting the acid derivative into acid itself. And believe me, it is one of the simplest reactions you have. You do just hydrolysis. You take any of the acid derivative and you do hydrolysis. So by the hydrolysis of acid derivative, you can directly obtain carboxylic acid. Remember like this. Whether you take acid chloride, so acid chloride is acid derivative. If you do hydrolysis, the Cl will be removed, you get simple carboxylic acid. If you take ester, you do hydrolysis, right? The OR dash part will be removed as alcohol, you get carboxylic acid. Right? You take anhydride, any of the acid derivative you take, the logic is very simple. You take the acid derivative, you do the hydrolysis simply, and in this case, if both alkyl groups are same, you will be getting two molecules of same carboxylic acid. If you have different alkyl groups, then you get two different carboxylic acid. So any acid derivative you take, chloride, acid chloride, ester, anhydride, right? Even amide, right? By the acidic hydrolysis of amide also you can prepare what? Carboxylic acid. So any acid derivative, when it is hydrolyzed in acidic medium, you get what? Carboxylic acid. And that is a preparation method for our carboxylic acid, right? Now, can you answer this question, all of you, quickly? Pause it, do it by your own. And if you want, you can answer in the comment box. I will check your answer personally. Select the incorrect reaction among the following. So, in the first case, you have acid chloride, you are doing hydrolysis, you are getting acid. This is quite fine. You have amide, instead of hydrolysis, you are treating with LiAlH4, which is a reducing agent. Now, amide, when it is reduced by LiAlH4, you will see this in your amine chapter, that with LiAlH4, this carbonyl is reduced into CH2. So you won't get COH here. COH you will get if you do hydrolysis in acidic medium. If you are treating with LiAlH4, in that case, you will end up getting CH2NH2, which is an amine. So that's the correct product. Now they are asking select the incorrect reaction. So definitely B is incorrect. And for the rest of the one, if I take 1 degree alcohol and I do strong oxidation with KMnO4, I will get acid. This is correct. Again, it is 1 degree alcohol, Jones reagent, CrO3H2SO4, acid. So reaction A, C, D are correct. But in B, we have the incorrect product. By treating amide with LiAlH4, you can't get carboxylic acid, you will get 1 degree amine, primary amine. So answer will be B because B is incorrect. And this question again, students, we got in the NEET 2024 examination. So again, a very recent question you have, right? Now, We are done with the preparations of carboxylic acid, but in carboxylic acid also, just like your aldehyde ketone, you will have to talk about a little bit regarding the boiling points and solubility. Why? Because when you compare the boiling point of your carboxylic acid, so it is higher than corresponding aldehyde, ketone, hydrocarbons, ether, and even your alcohol, right? And of course, this comparison is there when you have similar molar mass. So you have a similar molar mass acid and similar molar mass of aldehyde, ketone or alcohol. If you compare, then your acid will have higher boiling point. Why? Because carboxylic acid, it has a very, very high intermolecular hydrogen bond. And because of high intermolecular hydrogen bond, most of the time it exists like a dimer. It exists like a dimer. Even in the vapor phase, you will notice that because of intermolecular hydrogen bond, it behaves like a dimer, right? So because it behaves like a dimer, it has a very high boiling point as compared to aldehyde, ketone, alcohol, ether or hydrocarbon of comparable molar mass. And the rest 2 points, it is common in every chapter, right? That with number of carbon, your boiling point will increase, and with branching, your boiling point will decrease. Also, one more point is there. In your carboxylic acid, up to 9 carbon, you will notice that they are colorless liquid. If possible, you can remember this also, right? But after 9 carbon, right, from C10, C11, C12, they are solid and they looks like waxy solid, right? These colorless liquid from C2 to C9, sorry, from C1 to C9, they are having unpleasant odor. But in the solid form from C10 to above, right, they are odorless. So there is a difference in the odor, right? The lower members from C1 to C9, they have unpleasant odor, and the higher members from C10 and above, they are odorless, right? C1 to C9 are colorless liquid, and from C10 and above, they are waxy solid, correct? Now, talking about the solubility, the first 4 members of your carboxylic acid, they are pretty much miscible with your water, because again, they can form hydrogen bond with water. They can form hydrogen bond with water, right? With H2O molecule, they can form hydrogen bond. But with increase in number of carbon in the alkyl group, right? With increasing number of carbon in the alkyl group, because this is hydrophobic in nature, alkyls are always hydrophobic. So when your hydrophobic part will increase, its size will increase, so then your solubility will decrease. So you can say like this, that in carboxylic acid, when your alkyl group, the size of alkyl group increases, so with that the solubility decreases. So these 2-3 points regarding the boiling point and solubility you should know, because sometimes you do get questions in your examination, and let me show you what type of questions you do get in your examination. Can you do this, all of you? Carboxylic acids have higher boiling point than aldehyde, ketone and even alcohol of comparable molecular mass. Why? Because of formation of intramolecular hydrogen bond? No. Formation of carboxylate ion? That can't be the reason. More extensive association of carboxylic acid via van der Waals force of attraction? No. Formation of intermolecular hydrogen bonding? That should be your answer. You know, inter are different, right? Here we are having intermolecular hydrogen bonding, not intramolecular. And always intermolecular hydrogen bonding will be responsible for increment in the boiling point. So answer will be D here, of course, and this question from the physical property we got in the NEET 2018 examination. Correct? So after boiling point and solubility, now it's the time to discuss the chemical reactions of carboxylic acid, right? So first reaction, because you know that carboxylic acids, they are acids, so they have acidic nature. They can give H plus in the solution, they can give H plus ion in the solution. So they can react with both metal as well as bases, strong bases, right? If you take a carboxylic acid, right, so it can react with metal. With metal, it will produce salt and hydrogen. Just like inorganic acid, it reacts with sodium to give sodium carboxylate with H2. It can react with bases like NaOH, KOH. It will show neutralization here. Again, it will give you salt, but this time, okay, in above not H2O, it is H2 with metal hydrogen. And with NaOH, it will give you what? H2O, right? And I hope you know that carboxylic acid can react with basic salts like NaHCO3. And please remember that NaHCO3 is used to test carboxylic acid group, right? NaHCO3 is used to check whether your compound has COH group or not. Because with NaHCO3, carboxylic acid can release what? CO2. But all these reactions, they show that carboxylic acid is acidic in nature, right? Now, let's talk about the next reaction. And this reaction is very, very, very important for you. Very important. Dehydration. First of all, let me tell you that dehydration of carboxylic acid you can compare with dehydration of alcohol. Remember that dehydration of partial dehydration of alcohol in which you get ether. Similar kind of dehydration you have for carboxylic acid. Like two molecules of carboxylic acid together they can interact, and from one of the molecule OH group and from other molecule H plus group will be eliminated as H2O, and later on this O minus nucleophile, it will attach with this carbon electrophile to give you what? To give you anhydride. Here you obtain RC double bond O, this part attached with this part O C double bond OR. So by the dehydration of carboxylic acid, you can obtain anhydride, which is acid derivative, which is an acid derivative. And here again, because dehydration is happening, so you can use H2SO4. But apart from H2SO4, the more famous one is P2O5, phosphorus pentoxide, right? So P2O5 can be used, H2SO4 can be used to dehydrate carboxylic acid into anhydride, right? Now, after dehydration, the next important reaction of carboxylic acid is esterification, and I hope that esterification you also have studied in your alcohol chapter, because esterification is a reaction between alcohol and acid, right? Or alcohol or acid derivative, right? So if you take a carboxylic acid, right? If you take a carboxylic acid, so esterification is example of SN reaction, right? In which carboxylic acid is there, alcohol, let's say R-OH, it functions like a nucleophile here, right? And it will attack on this carbon to liberate this OH minus, and this OH minus is replaced by this alkoxide R-O minus. Ultimately, your product is RC double bond O, OR dash with H2O. And I think from your 10th class onwards, you know one point, that this esterification, right? This esterification is a reversible reaction, right? This esterification is a reversible reaction. So overall, what you can see, that it's a SN reaction in which from the acid, the OH nucleophile is getting substituted by the alkoxide nucleophile, right? Now, after esterification, the next important reaction, right, of carboxylic acid is again SN reaction. These all are SN reactions. If you remember, you must have discussed reaction of alcohol with PCl3, PCl2, SOCl2. And I personally treat PCl3, not PCl2, PCl5. It should be PCl5. So I treat PCl3, PCl5, SOCl2 as chloride donor. With alcohol or acid, what they do, they will replace the OH group with chlorine. So point is very simple. You take carboxylic acid, you treat with PCl3. So with PCl3 will give you Cl minus, so that will replace the OH. The ultimate product will be RCOCl along with byproduct H3PO3. Of course, 3 molecules of this will react. And with the same carboxylic acid, if you treat PCl5, In that case also, you get acid chloride, which is acid derivative, but the byproduct will change here. The byproduct will be POCl3 along with HCl. And with SOCl2, also, you will get the same acid chloride, but here again, the byproduct will change. In case of SOCl2, the byproducts are SO2 plus HCl. SO2 plus HCl. Same reactions you must have seen with alcohol, right? When alcohol reacts with PCl3, alcohol gives you RCl, right? But the byproducts in case of alcohol also you have the same, right? But these all are SN reactions of your acid. These all are SN reactions of your carboxylic acid. Even the esterification, right, is SN reaction. So whether it is esterification, whether it is reaction with PCl3, PCl5, SOCl2, and even that dehydration, you can treat that as SN reaction. So these all reactions are example of SN reaction of carboxylic acid. And why carboxylic acid is giving SN reaction? Because carboxylic acid has the OH group, OH minus group, the nucleophilic part, right? Now, after all these SN reactions, the next reaction is important for us again, reaction with ammonia, right? And this reaction is also quite similar to SN reaction, right? Of course, it's not direct SN reaction, indirect SN reaction. Because carboxylic acid is acid, and you know very well from your childhood that ammonia is a base. So when acid reacts with NH3, so first you will have a simple neutralization reaction. This H plus will be donated to NH3. You will get a salt like R, C, double bond O, O minus, and NH4 plus, an ion cation. So this is a salt. But if you do strong heating of this, so then H2O will be eliminated, right? 2H plus from this part and oxygen, this oxygen. And after elimination, after dehydration, you get amide here. Now, if you notice, one by one, we have obtained the acid derivative. Like reaction with ammonia, by heating, we are getting amide. Amide is acid derivative. In the previous reaction, when acid treated with PCl3, PCl5, SOCl2, we got acid chloride. Acid chloride is also acid derivative, right? So point is, in the preparation part, acid derivatives, they are converted into acid by hydrolysis. And in the reaction part, one by one, from the acid, we are getting the acid derivative, right? In the previous reaction, in esterification, you got ester. Ester is also what? Acid derivative. In the previous one, in dehydration, you got anhydride. Anhydride is also what? Acid derivative. So in the reaction, most of the reactions are those ones in which you are preparing the acid derivative, whether it is anhydride, ester, acid chloride, or amide. So now, after reaction with ammonia, right, the next reaction we have is reduction. And of course, because it is oxygen containing compound, so you will have to see reduction, right? And point is, carboxylic acid, it can have two type of reduction. One is, if you do partial reduction of carboxylic acid with especially lithium aluminium hydride, I hope you remember that carboxylic acid cannot be reduced by NaBH4, but it can be reduced by lithium aluminium hydride, right? So in case of lithium aluminium hydride, the carbon of carbonyl of carboxylic acid, it will be reduced into alcohol, right? But at the same time, if you do reduction of carboxylic acid with some strong reducing agent like H2PD, or instead of H2PD, you can use red phosphorus HI. So with very strong reducing agent, this carboxylic acid group, it can directly convert into alkane, right? So for carboxylic acid also, we have two type of reduction. Partial reduction gives you alcohol, and strong reduction can give you alkane, right? Now, after reduction, the next reaction is decarboxylation. Now, this decarboxylation is important for you. After dehydration, the next most important reaction of carboxylic acid is decarboxylation. And some part of decarboxylation you may have seen in your hydrocarbon chapter also, right? First thing is, we have different techniques of decarboxylation. Decarboxylation means removal of that CO2 group. From the carboxylic acid. Now that can be achieved first by soda lime. If you remember, carboxylic acid, when it is treated with NaOH, calcium oxide, soda lime. So it removes that COO part completely. This CO part is completely removed. This R combines with H to give you RH means alkane. So this is one way of decarboxylation using soda lime. It simply removes the CO2 part and this hydrogen attaches with the alkyl group to give you alkane. One more way of decarboxylation is there, which is coal-based electrolysis. If you remember, if you take carboxylic acid or its salt, right, in which you have carboxylate ion. So when you do electrolysis, so by electrolysis, what happens, right? This CO2 is eliminated at anode and this R is converted into radical, right? So two R radicals, they will combine to give you alkane. So this alkane and CO2, it will be liberated at your anode, and at cathode in this electrolysis, you get H2. So either by electrolysis or by soda lime, you can do decarboxylation, right? And once you get RH, once you get dimer, RR, right? Due to formation of radical. But one more point is there. Sometimes decarboxylation can happen, students, without using any catalyst or reagent, simply by heat, right? But simply by heat decarboxylation is possible only when you can get a stable carboanion intermediate. Like suppose if I take this CH2, C double bond O, OH, C double bond O, OH. Now if I simply heat this without using any catalyst, any reagent, so when decarboxylation happens in a simple fashion, I'm not talking about electrolysis, in simple decarboxylation what happens? This CO2 will go out because you have a OH bond here. So this bond will transfer between carbon oxygen and this bond will transfer onto this carbon. So on this carbon, alpha carbon, you get a carboanion. Now in this case, the carboanion we are getting, CH2 minus, it is stabilized by the carbonyl group through resonance, right? So in your decarboxylation, by the removal of CO2, if you can get a resonance stabilized carbanion, in that cases, you don't require any catalyst, any reagent. Simply by heating, this CO2 will go out, and in this case, your product will be CH3, C double bond O, OH. You will be getting acetic acid. No need of soda lime in this. NaOH, CaO. But please remember, this will happen only when after removal of CO2, the carbanion you get, that carbanion should be resonance stabilized by some other group, like in this case. So sometimes simply by heating also, you can have decarboxylation. So decarboxylation by simple heating, or decarboxylation by soda lime, or decarboxylation by electrolysis. These three decarboxylations we have, and from all of them, you can get questions in your examination like this. Can you answer this, all of you, quickly? Quickly, consider the below reaction. You have sodium salt of acid treated with NaOH and some compound with heat. You are getting CH3, which is alkane, and the byproduct is Na2CO3. So what's the reagent here? So if you notice, in this reaction, what is happening? This CO2 is going out, this CO2 part is going out, and this CH3CH2 is converting into CH3CH3. So this is simply soda lime decarboxylation. And if it is soda lime decarboxylation, so we have NaOH here, so the other reagent will be calcium oxide. And if you look at the option, calcium oxide is given in the very first option, A. So A will be your answer here. And this is a question from, you can say, soda lime decarboxylation. And we got this in NEET 2021 examination. Correct? Now, the next, and I can say one of the most important and the only name reaction for carboxylic acid is HVZ. The full form of HVZ reaction is Hell-Volhard-Zelinsky reaction. Now, it is a reaction in which alpha hydrogen, alpha carbon is involved, just like your aldol reaction of aldehyde. So like this, by connecting these 2 points, you can remember that in HVZ also we have same concept like aldol. Here also alpha hydrogen, alpha carbon is involved. Point is, if you take a carboxylic acid which has alpha hydrogen. This is your COH group, so this is your alpha carbon, right? So if your alpha carbon has hydrogen, and when you treat that by red phosphorus and halogen like Br2 or I2, correct? So what happens, this red phosphorus acts like a base here, and this red phosphorus can remove this H plus, and then this electron will be free, it will be on carbon, so that electron can be taken by the halogen, right? So on the alpha carbon, the hydrogen will be replaced by halogen, and you will get this kind of product, alpha halo acid. This is called alpha halo acid. Alpha halo acid. And this alpha halo acid, if you treat that with ammonia and all, you can get, with ammonia, you can get alpha amino acid, right? We can prepare alpha amino acid from this alpha halo acid. But point is, conversion of acid into alpha halo acid, this reaction is a named reaction, and it is called as HVZ reaction, right? So for this reaction, again, you need to remember the reagents and catalyst, that is red phosphorus and X2, correct? Now, after HVZ reaction, I think at HVZ we are done with all the reactions, because this electrophilic substitution is just a formality. Everywhere it is there, right? In all of the chapters you will have electrophilic substitution reaction, because it is the reaction of benzene. So if you talk about your benzoic acid, again, so electrophilic substitution is going to happen not for COH, it is going to happen for benzene. So COH will act like a group here, and COH, again, it will deactivate, it will decrease the reactivity of benzene towards electrophile, and it is again meta-directing, right? Because it shows minus R effect. So any electrophile you take, whether it is bromination, right, alkylation, acylation, nitration, sulfonation, any electrophilic substitution reaction you do, right, every time the electrophile will be added on the meta position in your benzoic acid, right? You can take any example. So after this electrophilic substitution, now it's time to see some of the questions from the properties of carboxylic acid, right? Can you try this by your own, all of you? RCOOH with some compound X gives RCH2OH. Okay, so it's a reduction, acid converting to alcohol, and RCH double bond CH2 with X, H2O, NaOH, H2O2 is giving RCH2CH2OH. So it is a anti-Markovnikov product. Now identify X in the above reaction. Okay, let me tell you one thing here. With your carboxylic acid, if I use LiAlH4, so with that you can get alcohol. But apart from LiAlH4, there is one more compound which can give you alcohol, and it is B2H6. I hope you know B2H6 from the hydroboration oxidation reaction of alkene, right? You know very well that in the second reaction, when this RCH double bond CH2 treated with B2H6, so B2H6 in form of BH3, it will be giving you the addition product, which will be R, CH, one hydrogen here, single bond, CH2, boron here. And if you do further oxidation with H2O2, it can give you what? R, CH2, CH2OH. So this reaction you people know very well, right? In the preparation of alcohol, you must have seen this, right? Hydroboration oxidation. And hydroboration oxidation of alkene gives you anti-Markovnikov product. So answer is B here. Sorry, answer is A here, not B, B2H6. But point is, when you take carboxylic acid, so this carbonyl group can be reduced by that B2H6 also. How? In B2H6, you know that you have boron and you have hydrogen. So when carboxylic acid is treated with B2H6, it goes through addition. In one step, the boron will be added to oxygen, the pi bond will break, and the hydrogen will be added on the carbon. And this step will repeat, right? Repeat until you have only single bond around this carbon. So you can note it down that apart from LiAlH4, even B2H6, hydroboration of carboxylic acid, can give you alcohol as the product. So both B2H6 and LiAlH4 can do partial reduction of your carboxylic acid, right? So, and this question is very recent. We got it in NEET 2023 exam, right? Can you do one more? Can you do a matching, a simple matching? On the list one, you have substrate and reagent or catalyst, whatever. And in the right side, you have the name of the reaction. So it's a simple identification question, right? You have to identify the name of the reaction. So in the first one, benzene with CO, HCl with anhydrous AlCl3. If you remember, it is a preparation method of benzaldehyde, and it is called Getterman-Koch reaction, right? So A is matched with 2. Ketone having a methyl group with NaOX or X2NaOH, it gives you haloform, right? So it's a haloform reaction. So B matched with third. B will match with third. In C, you have alcohol RCH2OH with acid. So alcohol acid is esterification, that's fourth one. So C will match with fourth. And automatically D will match with first, because acid having alpha hydrogen reacts with X2 red phosphorus along with hydrolysis, gives you alpha halo acid, and that reaction is called HVZ. So D will match with 1. Now look at the options, in which case we have A2B3C4D1. A2B3C4D1. I think it's in the first option only. So answer will be A here, and this is a direct question from the identification of name reaction. Answer is A, and we got this in the NEET 2021 exam, right? So point is, we saw the preparation and reactions of carboxylic acid, and you will get questions from them, definitely. But point is, there is a topic which we should never skip, and we should always study that topic separately, which is acidic strength of carboxylic acid. We know that carboxylic acid has acidic nature. Now for different carboxylic acid, the acidic strength will differ. Point is, if you take formic acid, if you take acetic acid, right? If you take propanoic acid, so all of them are acidic, but they will have a difference in the acidic strength. First point is, in your carboxylic acid, as number of carbon increases, so these carbons, these alkyl groups, they will show plus I effect with your carbonyl. Means what? These ethyl groups, methyl groups, right? They will show plus I effect, and plus I effect or plus R effect, you know very well that plus I plus R effect increases the electron density of carbonyl, right? And if it will increase the electron density of carbonyl, so that will decrease the acidic strength. So in your carboxylic acid, right, in the alkyl part, when number of carbon increases, your acidic strength decreases. So formic acid is more acidic than acetic acid, and acetic acid is more acidic as compared to your propanoic acid, and so on. As number of carbon in your alkyl part will increase, the acidic strength will decrease, because plus I effect will increase, right? Now apart from this, sometimes you do get question from the minus I effect also. Like suppose, if I take this compound, CH2F, COOH, CH2Cl, COOH. Now in these two, just for comparison, if you notice, on the alpha carbon, in one case we have fluorine, in one case we have chlorine. Now fluorine, chlorine, they shows minus I effect, and minus I effect, you know that it is more for fluorine than chlorine. And minus I effect will decrease the electron density of carbonyl or COH group, so it will increase the acidic strength, right? So more minus I effect means more acidic in nature. So in this case, the first one will be more acidic than second one. So overall, I think these points you know from your GOC chapter also, from the basic organic chapter also. And you should know that which group shows minus I, which group shows plus I, minus R, plus R. Because minus I and minus R effect will increase the acidic strength, while plus I plus R effect will decrease the acidic strength, right? Not only in the open chain, sometimes you do get questions for the aromatic acid also. Like suppose, if I have this benzoic acid, simple benzoic acid, let's say it is 1. I have this benzoic acid attached with methyl group, and I have this benzoic acid attached with nitro group. Let's say it is second, it is third. Now out of these three, the most acidic one will be third. Why? Because in third we have nitro, which shows minus R effect. then it will be first. Why? Because in second case we have methyl group which shows plus I or plus H effect, and plus I plus H will decrease the acidic strength. So as compared to methyl substituted benzoic acid, simple benzoic acid will be more acidic. So least acidic will be second one, right? So by groups also you get questions on for the comparison of acidic strength. So in your carboxylic acid, always revise this topic of comparison of acidic strength. Now, on the basis of that topic, acidic strength, can you answer this question, all of you, by your own this time? Pause it. Try to do it by your own. The correct order of decreasing acidity of the following aliphatic acids. So one by one, if you check, formic acid, acetic acid, then here we have more carbons in the carbon chain, alkyl group. Here we have even more. So you know very well that as number of carbon attached with your COH group increases, the acidic strength decreases. So here A is the answer, right? It's in sequence already, right? Formic acid is most acidic because in this case with your COH group only hydrogen is attached. Then COH, because in this case one carbon is attached. Then in this case you have total 3 carbons, and in this case you have total 4 carbons, correct? So because from left to right plus I effect increases, so acidic strength will decrease, and answer is A. And this question is very recent for us. We got it in NEET 2025 exam. So please never skip the comparison of acidic strength of carboxylic acid, right? Now let's do one more question. Can we? The correct order of strength of carboxylic acid. Okay, here if you notice, we have 3 structures. In first one, we have cyclic cyclohexane attached with COH. In second case, we have cyclohexane, but we have oxygen here. And oxygen in open chain or ring, it can show minus I effect. Please remember, right? And here also we have cyclic ring, but it is heterocyclic ring with one oxygen. Now, if you notice, in these two, in second, third, we have oxygen, so that oxygen can show minus I effect. In first, we do not have any oxygen in the ring. So in first case, we do not have minus I effect. So one thing is clear. Because second, third has minus I effect, second, third will be more acidic, and here the least acidic one will be first, right? And you know that inductive effect is distance dependent, right? So in first case, in second case, if this is your COH group, so this is your alpha carbon, this is your beta carbon. So oxygen is attached on the beta carbon. In the third case, if this is alpha, this is beta, this is gamma. So in this case, oxygen is much more near to COH group. It is attached on beta, and in this case, it is far. So if it is near to COH, it will show more effect, right? It will have more impact on the acidic strength. So second will be more acidic as compared to third, and the order should be 2, 3, 1. If you check the options, 2, 3, 1 is there in option B. So B will be your answer, and yes, it is. And we got this question in NEET 2016 examination. So now I think after this session, right, you need to revise. I hope that you people always keep your notes with you, right? Because in the organic chemistry, for each and every chapter, notes are very important, because you need to revise organic. Each and every chapter you should revise after a week or 10 days. Within 10 days, you need to go through the chapter completely, because then only you can memorize all those name reactions, mechanisms, reagents, right? Logical points, reasoning points, acidic basic comparison, everything. So if you have your notes, go through that notes, right, after this session. And also do not forget to practice questions, and you know very well that you can get the questions in the description of the video, right? We are providing it, and in those DPPs you can find all types of problem. So if you complete that DPP, you can be sure that you will do the question of examination also, right? And those DPPs you can also get at PW app. So download the app and start practicing, right? So that's it in this video from my side. I will meet in the next video. Till then, bye bye, over and out. Take care.